is. And so this is the ideal platform to exchange. This year we couldn't meet in person. That means we can't actually talk at the whiteboard, which is what we would have liked to do. On the other hand, we have already 71 people in this channel. There were about 250 signups, and so that's a big number that we have not anticipated this way, and that's the positive things that came out of having to do this virtually, as you can imagine. Like I said, it is about you. Before I get to that, the organization, you see we have 3 sessions, and we'll get to those in 2 seconds. The important part is that the talks in those sessions are scheduled so that we should be done with all the talks about 15 minutes ahead of time. So there is ample time afterwards for a discussion between the panelists, you know, with the audience. Keep your big picture questions to that end. Ask maybe a technical questions right after the talk, and then we can have a bigger conversation, a little bit off from what a typical conference schedule would be. So that's one thing. The other thing is look at the audience, and just to remind you, this is a very, very diverse audience from many perspectives. One, the backgrounds. The backgrounds is going from, you know, graduate students all the way up to faculty, and then also from, you know, university backgrounds to private companies, all the way to CTOs, managers, project managers, and also a lot of colleagues at research labs, LBNL, PNNL, ORNL, and so on, that are, you know, leading the way and doing a lot of projects in this field. And so what I want to remind you is when you're discussing it, you know, the audience is very diverse, and so keep that in mind when you're addressing questions and when you're answering those questions. One question that we ask you ahead of time is what you expect out of this workshop. And, you know, I was trying to make a really interesting way to visualize that, but the word cloud only showed reinforcement and learning. And so I removed that, and I just kind of just show you a few of these outcomes in the video. And you can read them. A lot of it is, you know, learn more. But a lot of it is also very specific. You saw their reward shaping going up there. Some of it was how do we apply this in my specific field. Some of it is, you know, specifically in building control. And so a lot of questions, a lot of good questions. And so I think the seeds have been laid for a very good workshop. And so with that, I would like to thank you for coming. I would like to thank you for attending. Thank you for submitting your papers. And I'll pass it on to June, who will walk you through the program. Thank you.
Thank you, Dr. Nagy. So together with Mario and Bing-Chin, we TPC chairs try to review papers and make a good program for the RLM workshop. So basically, 2 reviewers thoroughly reviewed each paper, and we selected 12 papers and then grouped them into 3 sessions. So the right side, I just make a word cloud map based on the abstract submitted from that total papers. As you can see over there, on the top side, electricity demand as an application side of this RLEM. And then the bottom side, of course, you can see RL as a big chunk. And then there's a HVAC and some technical terms like more state and reward, action space, state and action space. Those keywords are also popped up on the top. And then in the middle is a problem, like solving this very dynamic problem. And then there's a software and water and some technical keywords in the bottom. And we would like to thank all the technical program committee members for your spending time on reviewing those papers. Those 13 people, really great. Next, please. Yeah, so the 3 sessions are, first is a demanding response. As I said earlier, it's more on application side of how to coordinating the electrical grid. And next, please. And the second theme was clash of algorithms, which is more focusing on some theoretical part of algorithmic side of the this RLEM field. Next, please. The third one is keeping it real. And when we apply RL into energy management system, what kind of some challenges related to more like field implementation or software implementation, and those papers are addressing those things. And we would like to also thank all the contributors, authors, and co-authors of these papers to this great program. Next, please. So as a reminder for presenters of each paper, please change your Zoom name as session number and your name so that our technology chair can make you co-host so you can share your screen easily. So please do that if you're a presenter of those 12 nice papers, great papers. Next, please. All right, so it's now time for group photo time. So please turn on your camera and make a smile so that we can capture all your beautiful faces.
Kingsley is doing the pictures. Kingsley, you have to tell
oh yeah, so
when you're ready.
Can you remove the slides, please, so that I can get the whole gallery view?
Not a requirement that you open your camera if you're not ready for it, because it may be too early or too late for some people. It's okay, but if you can.
All right, smile, please. Thank you. I think I have everyone in the.
Okay, awesome. Thank you, everyone. Appreciate it. And we'll share it later in the Slack channel for everyone. And then let me move back here. Okay, then Mario, the floor is yours.
All right, so before I introduce the speaker, can I ask Kingsley or someone to bring him up as a panelist and ask that he can share his screen and also enable his video?
I have my video on. It was like, as it happened, right before I took the picture, like my camera stopped working. And so I was not in the picture, sadly, but.
That's fine, that's fine. Thank you. Well, so I'm very.
I can't share my screen right now.
We have your pictures, Iko, no problem.
So I think you should be able to share your screen.
I've made you co-host. Did you get a notification, Dr. Zico?
I have not been co-host, no.
How about now?
Oh, now I am, okay.
Okay.
All right, yes. I can share screen now.
Great. So it is my pleasure, my real pleasure, to introduce Zico Coulter. Zico is a faculty member in the computer science department at Carnegie Mellon University. He also is a chief scientist for AI research at the newly created Bosch Center for AI. That has many locations, but there's one in Pittsburgh, which he's leading. And he does a lot of interesting work. I think there's certainly very little time for all the questions that I'm guessing will come up after his talk. I know Zico from way back. We started working on non-intrusive load monitoring together, or at least at the same time, not necessarily working, collaborating together. And I personally appreciate all of the work that he's putting out. I'm sure that you guys will. I don't think that there's any more to say other than wait and hear everything that you will be talking to us about, Zico. So floor is yours. Take it away whenever you like.
Great. Well, thank you very much, Mario. Thanks to everyone for having me here. And I'm going to talk today about a very recent paper we have. This paper We put on archive, it went up on archive last night. It's been around for a while longer than that, but that was the deadline. I told them they had to get it before the conference, before the presentation today. So this is also the first time I am talking about it. So that, you know, forgive any bugs and such in the slides. As you know, when these things happen, there's some kinks sometimes. I'm still testing out how we're gonna exactly present all of this, but do feel free, I should add, to ask questions during this time. I would rather in the chat or just speak or raise your hand in the participants. Probably the chat's the easiest, actually. I'm pretty good from classes at looking at the chat while I'm presenting. So ask questions as I go. It is more important that we have a fun discussion than that I get through all my slides. That's the more important thing. And that I convey the basic ideas of what we do. And so if you're confused, as chances are a lot of people are also confused. So please do. That being said, there is some sort of dense math at times here. Some of it's kind of in jest almost, because I like to poke fun at how complex robust control is. But there is some math that is sort of pertinent to our actual approach. So I do want to if there is some confusions there, I'm happy to go through it, but I will try to pop out sort of regularly and also address the high level kind of concepts of what we're actually talking about here. All right, so actually the most important thing to mention is that this is joint work with two of my students, Priya Donti and Mel Roderick. So this is you can see my mouse, right? It's not ideal, but it's going to have to act as a cursor for now, or as a little pointer for now. And Mel Roderick, as well as a collaboration with Mayar Fazliab, formerly at UPenn, starting a faculty position at Johns Hopkins shortly. All right, so I am going to start out at with a pretty high level, and ask and talk about deep reinforcement learning. Right, this is a conference on reinforcement learning, and so I want to talk about what deep reinforcement learning has done, because it's done some pretty amazing things recently. This is why, to a certain extent, we're all here, right? So some of it's going to be a very biased sample of things, but deep reinforcement learning has done some amazing things. 2015, there's a famous Nature paper. Actually, the result was in 2013, but 2015 it was a famous Nature paper on learning to play Atari out of DeepMind, and so they learned to play all these Atari games from using a deep Q learning system. Later on, that same team, I keep losing the ability to go forward here. Yeah, okay. That same team famously defeated, same company, right? Different team there. Famously defeated one of the sort of masters of the game of Go with their AlphaGo system. And so this was an advance that I think was seen at the time as being maybe 10 years away. Computer Go had been progressing sort of slowly and steadily up until that point. And all of a sudden in 2016, there was this major breakthrough where a system also using deep reinforcement learning beat, he wasn't quite the world leader right then, but I think he was like number 4 in the world, but beat one of the best players in the world. And since then has improved even more to sort of be really unbeatable by humans. And then maybe you could always claim that, oh well, Go is easy. Because it's still fully observed, the full state, etc. But there's been other very cool things as well. So OpenAI in 2019 released a deep RL system that played the game Dota 2. I don't know what that even stands for. It's like a real-time strategy game like Warcraft. And by again using basically pretty straightforward conceptually, though of course there's a lot of complexity in the system, but conceptually kind of straightforward deep reinforcement learning algorithms, they were able to kind of get state of the art on a long time horizon, imperfect information, strategic multiplayer game, which is sort of one of the hardest classes of games to a large extent. And so the question sort of is, if we have all of this stuff here, why isn't deep RL being used kind of everywhere, right? These are really, really hard problems. And so why isn't deep RL kind of finding application everywhere? We have a lot of control tasks in buildings and a lot of other control systems. Why isn't deep RL being deployed there? And so, if it's so great here, There's a lot of tasks that we like to solve better. Maybe they're already kind of solved, but we'd like to solve them better. So, you know, what's stopping us from doing, hang on here. My cursor is not advancing. What's stopping us from using, you know, DeepRL for, I don't know, control surface control for airplanes, right? We have pretty good stabilization systems for airplanes already. They fly pretty well, right? They don't fall out of the sky, but you know, they can be improved. Certainly, we can make them more efficient, things like this, right? So why isn't it being used there? And I think the answer is actually sort of pretty clear also, right? So when it comes to sort of deep reinforcement learning, and reinforcement as a whole, right, it really is operating on a different paradigm than sort of we're used to in a lot of control tasks. And so a lot of control tasks, you know, what we associate with DeepRL are things like performance, but also things like exploration, right? So we don't know the system. We have to explore the system to figure out, you know, what's going, what does what, and what goes wrong. And we also associate it with very expressive policies. So control policies that can do, you know, almost anything with very deep networks and then things like this. But for which it's extremely hard to provide any guarantees. And we can contrast this with a system that does work in kind of modern, you know, aviation, but well beyond that, which is this sort of broad domain of robust control. So these are not new problems, right? We've been controlling airplanes for more than 100 years now. And at least in sort of modern implementation of these things, we actually have very well-established methods for controlling them, right? We have, you know, methods from PI control and robust control and these kinds of things that really work pretty well for those tasks. And what's associated with these things, besides of course the fact that control theorists also create much worse looking graphics than DeepMind, that's also a big difference. This is from, I think, Phil Koopman's course notes on robust control. But the things associated, that the goal of robust control to a certain degree are guarantees, right? And when you do control an airplane, you know, you really want to make sure it doesn't fall out of the sky accidentally, and you have to explore that, you know, 100 times before it actually starts to work, right? You really want to have guarantees about stability, about robustness. And typically it uses, to achieve this, it uses fairly simple policies like linear policies. So sometimes these are very different worlds, right? And they apply to very different things. DeepRL applies traditionally to sort of things that we don't really know how to solve very well, but we want to kind of turn over complete control to an algorithm, typically in simulation, let it run amok a whole lot and then figure things out. Whereas robust control applies to domains where, you know, we want to carefully characterize the precise level of uncertainty of the real system, solve that system with uncertainty to a degree where we can provide a guarantee of stability there, and then deploy that on the real system, but with much less chance, and still test it, of course, in the real system. It's not like we don't do any testing, but it can be much less testing because we sort of have to just validate that in fact the system does obey our assumptions about its uncertainty, and if we have that, then we kind of know that it works, and that's sort of the robust control paradigm. So what this talk is about kind of the middle ground between these two worlds here. So can we start to kind of explore the very wide space that lies between these two extremes? Okay. And in particular, I'm going to talk about how we can embed robust control policies within deep networks. So the talk's going to have 3 parts. I'm not even really bothering with sections here. I'll just sort of call out where I'm changing those. But first, to do this, I'm first going to talk about robust control. Then I'm going to talk about how we, and sort of what the guarantees of robust control are, because I'm actually working with a very specific type of robust control here, or we are. And therefore, I want to sort of define what I mean by that. Then I'll talk about how we can incorporate those same guarantees you have from robust control into neural network policies. And that seems actually somewhat surprising, right? It seems surprising that we can actually give the same level of guarantees as we have for a robust control system for a neural network policy. But it turns out we actually can do that. And once you do that, you can actually then train these things using standard deep reinforcement learning, while still having the guarantees of robust control. So this is the outline of the talk today. And I'll follow with some brief experimental results, but then probably more importantly, highlight some open questions at the end. Okay, so let's jump right in to robust control. So robust control is a field that's broadly concerned with methods that are certifiably robust to worst case disturbances within some specified disturbance region. And that's what robust control means. It means that the system will still perform well, even when it's being disturbed kind of in the worst case by some adversarial perturbation, as long as that perturbation is bounded in a specific way. So I want to give one example of these things, because I think it helps a lot to sort of be concrete with examples here, but it is going to be a little bit mathematical now. So one common example of these robust control specifications, or the kind of guarantees that we can get out of them, involves something called a norm-bounded linear differential inclusion. So it's a very simple system, actually, but it can capture very complex, potentially complex dynamics. So the idea here is that we have some states. So the state of our system is, I'm going to denote as xt here. That's the state of our system. It's the the angle of attack of the airplane, the speed you're going, or it's the whole game board if you're playing Go and things like those, right? It's the whole state of the system right now. And we're going to talk about continuous time systems here. I think that's actually sort of more common in traditional control. So we're going to talk about continuous time systems, meaning I'm going to describe the state evolution in terms of the time derivative of that state. So I'm providing a model for how the state evolves as essentially a differential equation, but because it's like a set, it's called a differential inclusion. All right, so the way we model a particular linear differential inclusion is to say that the time derivative of the state is equal to some linear function of the state vector plus some linear function of the control vector. The control could be how much you control the ailerons in the plane, et cetera, plus. And this, if it was just this portion here, this would just be a linear dynamical system, of which there are many techniques to analyze. But plus, we add this extra term here, which characterizes a potential disturbance that we apply to the system. And this disturbance can be really anything. It's not just random noise. It can be really anything you have. It can be any arbitrary disturbance, including sort of adversarial disturbances that try to penalize the system as much as possible. But the key point here is that in most robust control specifications, and I should add there are a lot of these, right? There are a ton of these, like age infinity control does a slightly different thing. All these things do a little bit different. But the thing that you do in robust control is that you bound the magnitude of that disturbance in some manner. Okay, so one common way of bounding it, for example, would be to say that the magnitude of the disturbance is bounded by some function of both the state vector and the control vector. Okay, that would be sort of a standard way of doing that. Again, the details are not super important here, and there are also some additional assumptions, like the fact that the zero state here is sort of our code for our set point. So it's not, that doesn't mean we have zero velocity. It means that zero state is just sort of the nominal state of the system. So this is sort of modeling like divergence from the nominal state. And the big idea here is that in some sense, what we're assuming is that that this disturbance is bounded as some function of the state and control deviation, which is kind of reasonable, right? Because if you're right exactly at like the equilibrium point, that's sort of a stable point, you don't need to do anything. But as you deviate from that, nonlinearities kick in, noise in your controls kicks in. So all these things happen that kind of make the system deviate from this nice linear system that you would have normally. And so this is this formalism that captures that. Right? And the goal of robust control is to find a control law, which is basically a function mapping the current state to the control you should apply, that will stabilize this system no matter what the disturbance is, as long as it's bounded this way. And this is what, this is an oversimplification, of course, but to a first approximation, this is what robust control is about. Of course, many different formulations, many different extensions, partially observable systems, all this kind of stuff, but this is what robust control is about. Any questions so far? I haven't seen any yet, but please do chime in if you have any questions. I'll bring the chat window back up so I can make sure I can see it. All right, so let me then move on. All right, so how do we do this? How do we construct a control law that is actually can stabilize this system here? Well, here's how you do it. Given this whole thing here, what you do is you solve this semi-definite program here. So this is a semi-definite program in some variables s, y, and mu. And then you solve this thing to be positive definite, and then you choose k to be, k is our control law. So k is the thing that maps states to controls. And then you choose k in this manner. That's right, so obviously. I'm putting this slide up, so this is kind of this is actually how you do it, to be clear. This is how you do it. You solve this semi-definite program. But the funny, I'm more putting this up as kind of as just a little bit of humor here, because if you read robust control papers, they're like full of these things. They're like full of these, like, they're called linear matrix inequalities, they're called or LMIs. They're full of these things. And they basically all describe conditions under which you can guarantee stability of a system under slightly different variants of this kind of thing. So I do want to highlight a little bit what's going on in this. I'm not going to derive this thing because it actually, I mean, it's quite involved, to be honest. It uses this thing called the S procedure and lots of sort of various semi-definite programming techniques. But really is actually what's going on here is quite simple, believe it or not. So what's going on here is that all these methods, and every time you see one of those big LMIs, those big semi-definite expressions, all that they're trying to do in all these things is construct what's called a Lyapunov function. So they're trying to construct a positive definite function. That just means this function is positive everywhere except 0 at 0. So it's constructing a positive definite function that is decreasing along trajectories of the system. Okay, so what that means is there's this function v. And by the way, the v that you get on that previous one is one of the variables was s that you're solving for, and v is just the quadratic form in s. So it's solving for Lyapunov function, and this function, you know, by definition here, this function is always going to be positive, right? So for any state, this s here is a positive definite matrix. So it's so this function here is positive no matter what. And the other thing that's happening here is that for any possible disturbance, this function will be decreasing. So what do you think about that is that this function is like sort of like a bowl that measures some notion of energy of the system. And this controller is always decreasing this function. In other words, it has to always be pushing the system to the 0 state. Okay? So if it's decreasing this function, then it's always going to be, you know, pushing the function towards, or pushing the state towards 0. And that's what all these big expressions are for. They are ultimately for ensuring that there exists a valid Lyapunov function for the state. So really, when it comes down to it, what robust control really does is it says, given some uncertainty specification, like this one I gave a few slides ago, given that we're describing a system like this, can we find a Lyapunov function, a function that sort of measures some notion of energy of the system, such that this function, we can find a control that always makes this function decrease. And this function is always positive, and so therefore it always, you know, goes to nicely drives the state to 0. But you don't have to worry too much about sort of, still you don't have to worry about the form of this function, but this notion of stability as dictated by a Lyapunov function actually is an important one. And this is the key thing that we're going to use to ensure that deep reinforcement learning policies can also be guaranteed to be stable in the same way. And that's the core idea that we're going to exploit here. So before I do that, I want to make one, I sort of mentioned this before, but I want to make one sort of important note here. In that I'm writing our system as in sort of in this form. So I'm writing our system as, you know, x dot is in this thing here. And I'm also assuming that, you know, A, B, G, as well as the other elements, by the way. So a few points. So, you know, going back to here again, you know, the things that characterize this system, right, where the matrices A, B, G, as well as things that characterize the bound, which are the C and D matrices, right? So these are all matrices because these are all vectors of the state and everything like that. And we're assuming that they're all known. So if you look at this LMI one more time, I promise this is the last time I'll have it up. But if you look at this one more time, it actually, there are terms that involve A, B, C, D, and G in there. So you have to know those things in order to solve this LMI. If you don't know them, this doesn't mean anything. So we're assuming that we know these here. And so the point that I want to make, though, is that assuming we know these matrices does not imply that we actually know the true underlying system, right? So the whole point about robust control is that we assume the true underlying system is not actually known, that it's some unknown system, and all that we really know here are bounds on that system, right? So in particular, this disturbance term that I mentioned before, this W term, it can represent things like, well, nonlinearities, even if we know those, I guess I still represent those because the system is linear here, other than the disturbance. But it can also model just unmodeled dynamics too, right? So we can kind of, whatever sort of things we don't understand about the system, we can kind of push into that W term. And as long as we're able to bound it, then we can still provide guarantees as to the performance of the system. And this is really the power of robust control, is that even without knowing the true system, you can still get guarantees about its performance as long as you're able to provide bounds for it. Now, you can't do this for every system, of course, right? If the bounds grow too big, there will not be a solution to that linear, like the optimization problem will be unsolvable. It will not have a solution. But for certain classes of systems, you can, in fact, provide a guaranteed stable control law and a Lyapunov function that will always work here. And that's the basic idea of robust control. So robust control, I mean, at this point, it sort of seems great, right? Like, I guess there's sort of this pain point of having to actually come up with these matrices, but I don't know. We know how to linearize systems. Maybe it doesn't really work for Atari, but that's sort of okay. It does really work really well for airplane control and stuff like that. Maybe we should just stick with it. But the question here, and I think really the motivating principle from DeepRL that's worth thinking about is, can we do better than simple robust control? Because importantly, robust control still is talking about linear control laws, right? We still have the control is still a linear function of the state. That's not very expressive. We know that nonlinear controllers can do much better at actually solving these problems than linear controllers. And I think every time someone enters the room, Zoom takes back over control of my screen because I'm a presenter now. So. And so, is this a job for DeepRL, right? Maybe if we want to have more expressive control laws, we should use DeepRL, and we should be using these things to actually solve for, the plane ailerons controls, modulo the fact that, again, we probably don't want to crash a bunch of planes before we actually can solve this. So that's the setting so far. So that's actually all you need to know about robust control. Hopefully I did not lose too many people here. Again, high-level points are there exist these very powerful methods that create control laws, but they are very simple control that guarantee stability, but they are very simple control laws. Any questions based upon that? No questions still. Okay. Everyone's like an expert in this stuff already. I'm just rehashing like the basics here. Move on to the more complex formalisms here. Okay, got it. All right. So this is a job for DeepRL. So the DeepRL paradigm is a little different, of course, than what we talked about so far. So in traditional deep reinforcement learning, you kind of assume the system is fully unknown. Right? So you don't know anything about the system. We can only observe the system through interaction. And given this interaction, we want to find a policy that performs well, right? Where well is defined by maximizing some reward function. And in DeepRL, typically this policy takes the form of some deep network. So a very simple definition of DeepRL, I guess, but it's pretty accurate also. And the unfortunate part is, if this is genuinely your setting here, you are a little bit out of luck, because if the system is unknown, you basically need to take potentially unsafe actions in order to explore it to the point where you can actually learn what to do. Right? If you knew nothing about the system, you can't do much. If you're just given an airplane and say, I don't know how anything affects it, stay in the air. You're probably not going to stay in the air at first. You're probably going to crash a few times before you learn to stay in the air. So we need some middle ground between these two things. And so this is why we actually are thinking about a modified setting that is actually the robust control setting. In other words, we actually assume the truth system is still unknown, but we know the exact same thing we knew from the robust control setting. In other words, we have a set of linear matrices, basically, or matrices here, that characterize the uncertainty of the system in the way you saw before. So the system is a linear differential inclusion with some norm bounds that depend, with the linear system depends on these terms here, and the norm bounds depend on these terms here, or some ordering of this. And the reason why this is actually legitimate, even though we're applying RL, is that this is realistic in many settings. We know that many cases we do in fact have a description of the system. And so we should use that in order to improve our performance. We shouldn't actually, whether you're controlling an airplane or a building, it would be crazy to throw away all the knowledge we have of these systems and just apply pure RL as if we didn't know anything about these systems, as if it was just literally a black box we had no idea, no concept of. And so I think there's actually, maybe as an aside, I think this is actually an important thing to consider in RL as a whole, is what are the assumptions we make about what's known and not known. And there are a lot of cases where we actually can assume a lot is known because we actually have that in practice. With that being said, though, the key question I want to address is, can we use reinforcement learning methods to learn a better policy than a robust control law while maintaining robust control guarantees? And I mean that, both while you're learning the system, so while you're running your RL algorithm to sort of learn the right control policy, and at the end of learning itself. And these are going to be this is going to be the main challenge that I'm going to ask here in the remainder of this talk. So the answer, as you might guess, is yes, we can. And I'm going to show you how to do that. So here's the key idea. The key idea is we're going to first, before we run reinforcement learning, we're going to run robust control. Okay, so we have all those matrices. We're going to run our robust control algorithm. We're going to get out a policy. We're going to get out the control, the gain matrix K, as well as we're also going to get a Lyapunov function that guarantees stability of that policy, right, under any disturbance. And then the cool part now is we can actually look at this Lyapunov function and ask the question, what are the set of all actions we can take for a given state that actually decrease the Lyapunov function? Okay. Because, and here, you just see the paper for these details. I'm going to try to highlight the main point here, but this is actually probably the tricky math that you do have to know a little bit. So I'll try to go through it in some detail. This is not a joke equation here. So here's what sort of the key idea here is. So when we have this Lyapunov function of a particular form, and we have the linear, the bounds on the system prescribed by this linear differential inclusion, we can actually analytically solve for what is the worst case, what is the largest possible increase you can have in the Lyapunov function over time. And we sort of denote this as V dot. That's essentially the time derivative of the Lyapunov function itself. That's how the Lyapunov function is changing. We want that to be decreasing. And so if the maximum sort of increase is greater than 0, then we're not decreasing anymore. Right? So we want this thing to be less than 0, basically. And by the way, actually this sort of form is the same way we derived that great big LMI before, but I won't. It's actually simpler once you already have the Lyapunov function substantially. So this sort of expression here on the left, this denotes the worst case increase in our Lyapunov functions under any disturbance. And we want this thing to always be negative. And if we apply some algebra, it's not very hard. It's one line of linear algebra or 2 lines of linear algebra. What we see is that we get a form like this. So it's some constant plus another constant times some vector plus d times this u term plus this term here. Of course, these constants depend on the actual state that you're in. This thing is for a given state, but for a given state, the worst case increase in the Lyapunov function looks like this. And the key part, the only part that's actually important here to note, is that this worst case increase is a convex function of the control input. It has a term that involves a L2 norm, a term that is linear, but this whole thing here, which I'm just going to abbreviate as S for like safe use, this whole thing here is a convex function. And that's actually a very generic thing. I mean, the reason why robust control is possible is because that thing is convex. And so for any reasonable robust control specification, this will be a convex function of the control. All right, so now we have the main sort of challenge here. We want to ensure that whatever our neural network policy outputs satisfies the constraint that this thing is less than 0. And if we can do that, we actually will guarantee that our policy will also decrease this Lyapunov function. So that is what we do. So here's the slide sort of actually showing what we do. So we're going to specify our deep policy as something that takes some arbitrary deep networks output. So this is like a normal neural network policy you would have. It's just some neural network function of the state, and just projects it onto this set of safe states. There's a little bit of details here. Like you can't actually have something that's less than 0 strictly. So you have to actually have it's a little bit strictly negative, depending on the size of the state, but don't worry about that. This is conceptually what we're doing. And because this is a convex function, the set of all points that for which this is negative actually in this case looks like a cone here. In fact, in the previous case, this is a norm term, so this convex set actually ends up being exactly a second order cone. But that's not an important characterization. Okay, so graphically, what this looks like is the following: we have some safe set here. We have the set of all controls that are safe. In other words, they decrease the Lyapunov function. We know there exists at least one element in the set, by the way, because we know that k times the state is in that set. So the set is not empty. It has some element to it. This is very important, actually. And we know that robust control tells us an element of this. Then the way we define our policy is we just take our arbitrary neural network function, which very likely will give us a point outside this set, right? Because there's no reason for it to be inside the set. It's a neural network. It could definitely be doing something unsafe, almost certainly. And we project it onto the set. And when we do that, now all of a sudden, this policy pi has all the guarantees that the robust control policy has, because that policy pi is still decreasing our Lyapunov function. And, sort of very cool, we can also apply any reinforcement learning algorithm we want to this new policy here. And the reason we can do that is we actually, though this is a little bit, I'm not going to talk about, okay, does the set only, okay, so for Mario, so does the set only include, no, so the set's actually bigger than just that one U. You can probably show this set it's not a singleton. It has, I mean, in the very least, you can have a scaling of that UT. That's sort of a cheating one, right? But you can just like pick the scaling of it. Okay. That's pretty lame. But it definitely is not a singleton set. It is a set that contains many elements, many of which are going to be better than the linear control law. Okay. And in fact, what you really want to do is sort of like, depending on your actual state, you kind of want to bounce around this whole thing, right? You want to bounce around this thing kind of arbitrarily in a nonlinear fashion to have the best control law you can have. And because of this, Yeah, so someone asked, how do you determine the projection function? The projection function itself is just the projection onto this set. And actually the projection function, because it is dictated by the Lyapunov function, that's determined, the actual projection part is determined entirely by the robust control specification. The cool part here is that we actually, and this is a long line of work we have actually on differentiable optimization. It turns out you can actually just like you can differentiate through a neural network to train it with backprop. You can also differentiate through projections. They are also differentiable operators. And it turns out you can actually treat this whole thing, this whole network, as one big black box policy that just happens to have its last component specified by robust control. Okay, so is the set of safe control the form that is easy for PGD? So just to clarify, we're not trying to use PGD to find the set of safe controls. We're using robust control to find the set of safe controls. And we're going to use PGD to train the parameters of the network of F here, which can be whatever we want. F can be as nasty as possible. Because it's followed by this projection, it will always project back into the safe set of safe controls, and therefore always lead to a safe policy, no matter how we train the parameters of our neural network using any unconstrained optimization method. Okay, so that's the key idea here. So let me just summarize this, because this is now getting, and then present very briefly our results, and then pause, and then end for the end of the talk, and maybe time for questions. I'm actually not sure. Do we have time for questions afterwards, or just during?
Yeah, we should have a couple of minutes for questions. Yeah.
Okay, so high level. Here's what we're doing. Okay, what's state action constraints? No, okay, state and action constraints, right? So for state and action constraints, we are assuming unconstrained for this linear differential inclusion in theory, but that disturbance term can actually capture strict constraints that you do impose on the states or controls. So you can actually have constraints on those sort of implied by the allowable disturbances. That's a different model than the simple norm bounded model. That's a different sort of robust control model, but you can have similar bounds on them there. Yeah, you can do that. Yeah, so they are, okay, this is the point I want to make. So do you consider nonlinear dynamics? Yes, they are nonlinear. That's the point I kind of want to make here, is that I'm writing it like this, but this is not an equality. This is an inclusion. W, our disturbance term here, can depend on anything. It can depend on the state, the control, anything in an arbitrary nonlinear fashion. So this system here can be unknown and nonlinear. We just are bounding it by this linear kind of over approximation of the system, which is exactly what's done in robust control. Those systems are nonlinear too, and everyone knows they're nonlinear. We're just bounding it with an outer bound of a linear system. And yes, we can start to say so using all those matrices, A, B, G, but also C and D, which are the norm bounds. Yeah. All right. So simple summary: solve robust control. Number one. Number two, use the output of the robust control law to define a safe set, or really a safe set of controls for any given state, and define the RL policy as an arbitrary deep network, can be whatever it wants, completely unconstrained, but then followed by a projection back to the safe set. When you do this, the resulting policy will have the same guarantees as a robust control policy, but can learn, ideally, better nonlinear control laws using RL methods. And that's the key idea here. So let me just give a few brief examples here. So I'm not going to spend too much time on this because I'm just going to show you a table next, but try to highlight some of the main results. You can check out all the actual results in the paper. I'll have the link again at the end of the last slide. Maybe I'll place it in the chat as well. So we ran, to be clear, simulated experiments. So we're just testing these things out in simulation so far. This is a sort of an initial study, certainly. But we did it on 4 different domains. just sort of random different linear differential inclusions to start with. So just generate kind of random A, B, G, C, D matrices, etc. But then some sort of common benchmark tasks like cart pole stabilization, quadratic control, as well as a microgrid simulation. I won't go into details of those things. Again, those are all in the paper. In all cases, what we compare is we compare how well the approach works under normal operations, as well as under kind of worst case adversarial disturbances as governed by these norm bounds that we have. So okay, I want to highlight the results here, but this is a big, massive table. I just want to highlight a couple. I'm going to blank out some stuff in a second and just kind of zero in on a few things. So let me sort of mention what I'm comparing here, though. What we compare across these domains is, first of all, sort of non-robust control, so non-robust LQR, which is a standard kind of control method, a classical control method, as well as MBP here stands for model-based policy learning in RL, and PPO is a standard RL method. But these are all sort of non-robust methods, both the classical control and RL-based. We also have a robust version of the classical control law, which is, again, uses this robust specification and then solves an LQR like objective separate from this. And we have sort of, using our method, we have robustified versions of these RL methods. And so I just want to sort of zoom in on one particular line here. And it's a little hard to read here, so I guess I should have explained this more, but O means an ordinary operations and A means adversarial operations. So like the worst case you could experience under any norm, under any disturbance to the state. And what we find are sort of two important things here. So we find that, first of all, our robust, kind of pretty much across the board here, and this actually is true for all the others you'll see as well. So across the board, our robust RL method under ordinary operation works better than the robust, like the classical robust control method. That's sort of number one. Does not work as well, by the way, as the non-robust. I mean, maybe LQR is sort of weird here. I guess this is an outlier here, but does not work always well as LQR. But under ordinary operation, I guess actually that makes sense too. Now to think about it. But it does work well. But what does work better than all of them under ordinary operation is RL. Right. So if you just apply normal RL with an arbitrary neural network policy under ordinary operations, that works quite well. So it works typically better than our kind of robust methods. Again, because it can do whatever it wants. It can kind of violate whatever constraints it wants and violate whatever safety it wants. But the big sort of second point here is that when we do actually have adversarial situations, our methods remain stable. Whereas traditional LQR will always, or traditional either LQR typically, but also typically RL methods will go unstable. They will basically blow up and the system will fail, hit whatever balance it has, etc. All right, so again, a high level, the nominal performance is better than robust control, and the worst case performance is better than RL. And that's the kind of guarantee that we have from these systems. So with that, let me have my last slide and just say the take-home message from this is that under a certain setting, we actually can incorporate robust control constraints into generic deep learning. But I think the work here is just getting started to a certain extent. First of all, we haven't really done anything real here. There's no real experiments here. We're just doing some simulation and seeing how this really works, especially in domains where we actually deploy robust control, I think is really the key step to getting this to actually work. But then maybe at a higher level, the last thing I want to kind of emphasize is I've set up kind of one middle ground between robust control and reinforcement learning. Other papers have done other kind of middle grounds, and there's a huge wide array of things that lie between these two extremes. And so part of my kind of hope for communities like this one, like the controls community and the RL community, right, interested in both sides, is that we find these middle grounds where we can kind of do both these things together. So thanks very much. Our paper is available here. Code is also available. would love to get anyone's thoughts and opinions, but thanks very much. Oh, and I'll answer a few questions now from the chat. But I also, Mario, whenever I need to move on, just tell me. I'll text after that.
Yeah. So actually, if you happen to see a question that you would rather answer for everyone, that's okay.
There's some very easy ones. So the performance numbers are arbitrary LQR cost matrices. So they're the actual numbers don't mean anything. All that matters is the relative scales. Yes, it can definitely use off policy methods too. So again, this is just a policy parameterization. So as long as you know bounds the true system, you can use whatever RL method you want, including off policy methods. PPO can be done kind of off policy too, but it's usually done on policy. And then how expensive is the to calculate the projection? The projection is actually very straightforward, and we run it. I mean, it's easily real time. It runs in a few microseconds. It does slow down the training a bit because even though it's fast, it's still not as fast as nothing. So it's actually microseconds is probably wrong, but definitely on the order of a millisecond. But it is not nothing, but it is very, very fast because it's solving a tiny projection onto a second order cone, which you can do really fast with some alternating projection methods. And that's basically how we do it. Why deep RL? Yeah, I mean, to be clear, I'm talking about RL in general, right? Like this could do with any RL method. Deep is just because with deep RL, it's like you have a more expressive policy, and it's traditionally been hard to impose constraints on that policy precisely because of its expressiveness. If you have a linear policy, you can kind of already do this to a certain extent. And so I'm really focusing on the cases where you have non-linear control policies.
Great. Well, we're going to have to move on, but I'm sure that there are questions here that will continue coming.
Yeah, I'll stay around there for a while and type it. I have to give an exam in 25 minutes, so I will. You don't
have to stick around if you.
But I'll stick around for a little while, and I better join that like 10 minutes early too. So I'll be here for 50 more minutes, and I'll answer questions in the chat.
Thank you so much, Zico. I don't think we could have asked for a better and more centered talk than this one.
Great.
Thank you so much. Yeah.
Thanks.
All right. I don't know how we do this. Round of applause virtually? I will do my applause here. Right, Zoltan or whoever is next, over to you.
All right, thank you, Zico. Very awesome talk. I would have one question, but I'll ask it in the chat so we can continue with the program. So we'll talk our first session. I will start the first session, and I'll hand it over to session chair Lucas Spanger from UC Berkeley, and I'll ask all the authors are identified, so you should have access to share screen. And Lucas, take it away.
Hello, everyone. Really nice to be here today, and thank you again to Dr. Calder for an awesome keynote. Some brief information about me. I'm a fourth-year PhD student at UC Berkeley. I'm in the lab of Costas Spanos, and right now I develop reinforcement learning for setting out prices for demand response throughout the day. And so, as everyone knows, reinforcement learning is tough, and dealing with humans is also very tough. And so the two together have been an interesting challenge. But it's awesome to be in a workshop that's geared towards generally a very similar area. The way that this will work is that we have 50 minutes in total. I'm going to introduce our first authors from the Technical University of Denmark, and the presenter is Morten Christensen. So Morten received his master's in psychology from the Technical University of Denmark in 2010. After 6 years in industry as a consultant and designer of automation systems, he returned to academia in 2016, and he's been working as an industrial PhD fellow under the supervision of Professor Pierre Minson. Working for more than 5 years on the Energy Lab Nordhaven project, Morten has extensive knowledge of the role of flexible consumption and intelligent buildings in integrating energy systems. So in terms of Morten's long-term research interests, they want to explore context-aware control, So in some ways, I guess, similar or along the same lines as the Keynote. They're looking to control buildings as a key source of flexibility. They aim to include knowledge of buildings and documents into deep RL based on controls to create building controls that are better, smarter, and greener. They love spending time with their kids, reading sci-fi, and of course, the very little task of saving the world. With that in mind, I'm going to hand the stage over to Morten, and Morten gets 7 minutes to talk and then 2 minutes of Q&A. Morten, please maybe have my video pinned so that like I'll hold up a sign saying like 1 minute left to try to keep you on time.
Okay, thank you very much, Lucas, for the lovely introduction. I'm very honored and happy to speak today. And it's a tough job following the keynote. That was extremely good and interesting. And let me start by giving you a very high-level introduction. So the energy systems are changing, right? From a situation where fossil-based power plants schedule and plan according to known or static loads to a situation where the roles are flipped and flexible loads are managed according to the production from intermittent renewable energy sources. So in this talk, I will present our results exploring two of these key problems within demand response. The first being price-sensitive control of a single building where electric-based space heating is made price responsive and sort of balances the cost and the user preferences. And the other is a coordination task where a population of such price responsive agents are then controlled by setting a price in order to manage a total load in the electricity grids. So one way to do that is through optimization. And here we have formulated a linear program with an objective function that includes the total energy cost and a thermal disutility that represents the willingness or the cost to transgress the comfort bounds of the user and subject to constraints that represent in a very similar manner the thermal dynamics of such a building in a linear model. When we translate that to a reinforcement learning setting, then the states we're looking at here are the temperatures inside and outside, the solar irradiation in the house, the price of electricity, and the time of day. The actions for the reinforcement learning agent is then the heat pump operation, and in a similar manner as for the linear program, we have formulated the rewards based on energy cost and the thermal disutility. So the nice thing about this, of course, is that we can solve the LP to an exact solution, and then we can compare to the performance of the reinforcement learning agent. For the bi-level problem or the coordination problem, it's a bit more tricky, and we still have the terms for the energy cost and the thermal disutility, but now we have included a cost that is the load violation disutility of such a demand response operator. So sort of his willingness to pay in order to keep the load Lmax between below some bound. The thermal dynamic equations of the building are the same, and then we fix the heat pump operation to the output of the reinforcement learning agents of the previous problem. And then there are some constraints as well on the total load limits. When we
solve that problem in using deep reinforcement learning, our new states are then the total unflexible base load, the temperatures outside and inside in the individual buildings. And the action for this problem is then a set of prices. Again, the rewards are based on the energy cost as before and the thermal disutility, and including this load limit disutility for the demand response operator. Going straight to the results, we and the case study, we compared the performance of pretty much vanilla DQN and DDPG to baseline, which is sort of a naive hysteresis controller, and then the ideal optimal baseline, which is the solution of the linear programs for the binary and the continuous case. And when we look at the results in terms of the total energy cost, we find that for the naive hysteresis controller performs worst as expected, with the highest total energy cost and the highest energy consumption. Whereas the two reinforcement learning or deep reinforcement learning agents, they perform almost as well as the ideal baseline. So when we look at the coordination problem, we had just a DQN agent that is compared to a static and a time of use pricing. And when we evaluate the results of those, we see that the reinforcement learning agents, the deep reinforcement learning agents, are able to manage the loads of the population of buildings better than the time of use, which is here in the green, but at a much lower cost. And while the static price is sort of efficient in managing the total load, it of course depends on the price that you set for the energy. So in summary of the paper, we found that this deep reinforcement learning framework to be a strong framework for this model-free control that could potentially release this flexible consumption in buildings. And while the deep reinforcement learning agents, they outperform our naive controls and with a performance that is approaching the optimal controllers. Our first step towards this full multi-agent setup solved the coordination problem and the lower level problem of price responsiveness was solved as well. Of course, in future work, we would like to explore the full simultaneous learning of multi-agent setup, but I think actually today we will have some interesting presentation on that exact subject. And I think that was what I had planned for my 7 minutes. I completely lost track of time, Lucas. I'm not sure.
Yeah, yeah. I think it's you were completely on time actually, and now I think we have 2 minutes for questions, and so I think we would probably take 2, and I'll limit each to 1 minute. If no one else has a question, I have one that I'm very curious about, and this is more of like a meta research question, and it was around how did you formulate the specific research question that you looked at right now? Like what were some of the challenges in trying to map out the technical details?
Well, I mean, for me, the reason why I think that reinforcement learning has such a promise, and I liked a lot what Zico said, and we shouldn't throw out the knowledge of the buildings on one hand, but on the other hand, for my application, which is I guess for flexibility, the value gain is quite the potential value gain is quite small, right? So I really enjoy this sort of black box or completely model-free approaches, because I'm not sure there's going to be people spending a lot of effort to incorporate knowledge of a particular building into the controls. Or I don't know. We will see. At least for these small low value loads, something that is more go out and explore is really appealing.
Sure. What led you to look specifically at water heating?
Well, this is actually based on space heating of using a heat pump, right? So in Denmark, we're seeing the electrification. When we want to use all this renewable energy, then electric heat pumps, they're just a very nice thing in that they couple sort of the electricity system to a huge source of flexibility, which is our built environment, right? So we can store quite a lot of energy in the buildings potentially that we would otherwise have to buy batteries or other forms of storage for.
Yeah,
that's sort of the motivation behind that.
I agree, and as far as like a latent state goes, it seems to me that water heating is particularly well applied to reinforcement learning that helps model these latent states. I have a question from Nicholas Fatris. Nicholas, do you want to ask it yourself, or shall I read it?
Yeah, sure. I can ask it if you guys can hear me.
Mm-hmm. Yeah.
Yep. Basically, I was wondering if the market prices were taken into account in your kind of reinforcement learning, and if they were trying to adapt the heating strategy based on when the market prices were highest or lowest.
That's the lower level problem exactly. Yes, then that is what the price responsive behavior is learned exactly using spot market electricity prices. Correct.
All right. Well, please join me in either a virtual clapping reaction or a physical clapping reaction, because for a fantastic presentation and the difficult presentation of being right after the keynote.
Thank you very much, but I'm very happy to have the opportunity to learn with all you today, and I'm looking forward to the rest of the program.
Now it's my honor to introduce a group from Oak Ridge National Lab on electricity pricing aware RL-based HVAC. It's an extremely technically interesting paper, very thoughtful, very well written, and so I'm looking forward to the presentation a lot. So the presenter is Kurt, I believe, right? And so sorry. Kurt is a research scientist in the Computational Urban Sciences Group at Oak Ridge National Lab. He finished his PhD in image information mining from IIT Bombay, India, which is out of the IITs in India, many consider it to be the best, although I think IIT Delhi would probably contest that. During his PhD, he generated an interest in fields of machine learning and high performance computing for various geoscience and remote sensing applications. After his PhD, he joined Oak Ridge as a postdoc researcher in scalable geocomputation in January. His long-term research goals are to contribute towards the betterment of society by conducting applied and computational research and development in urban sciences. His specific research goals include conducting data-driven research for urban mobility, geosciences approaches in transportation, and data-driven approaches for energy optimizations in buildings and smart controls. Personally, he loves badminton, cricket, and reading books, and listening to Indian Bollywood music. And my first question before the talk even begins is who your favorite Bollywood artist is?
Thank you, Lucas, for that beautiful introduction. So I'll start with your question. So do you know Shah Rukh Khan?
Yeah.
Yeah. So that's my favorite actor. Yeah. All right. Let me share my screen. Okay. Is it visible, Lucas?
Yep. You're good.
Okay. All right. Then I can start. Hello all. I'm Kuldeep Kote. I'm research scientist in Oak Ridge National Laboratory. The title of my talk today in RLEM workshop is Electricity Pricing Aware Deep Reinforcement Learning Based Intelligent Control for HVAC. The specific focus of our work is to explore how well-crafted features from electricity pricing can improve observability and the performance of RL agent. So before I begin my talk, I would like to thank my collaborators and also our sponsors, US Department of Energy, for funding this effort. This is the outline of my today's talk. Let me begin with a few facts. So buildings are the major consumers of energy in the United States with over 40% of total energy consumption. The International Energy Agency estimated around 30% of growth in building energy demand by year 2035. As per Energy Information Agency of US, over 51% households total annual energy consumption in the year 2015, although was attributed to HVAC. So from these facts, it is evident that the intelligent HVAC control can significantly reduce the building energy operation cost, as well as help us to minimize the environmental impact by reducing the peak power usage. So in literature, during last few years, there have been many efforts in developing intelligent HVAC control. So we can categorize those efforts in three broad categories. One is rule-based approach, where we encode rules. So this kind of approach needs very specific and detailed domain knowledge so that we can include generalized rules to perform better. Then the second category is the model-based approach. For that, we assume that we have understanding of the model of the environment. In case of MDP, we have transition probabilities kind of understanding. Examples are model predictive controls, and as I mentioned, we need accurate building model to achieve good accuracy, and those approaches are also computationally expensive. Then third category is the model-free approach, which does not need the understanding of the environment in terms of model. Examples are Q-learning approach, and those approaches learns using the continuous interaction with the environment. As Keynote also mentioned, and I'm also reiterating that the deep neural network showed human level performance in playing Atari games in that, and they showed that result in their Nature paper. They used neural network to approximate the Q tables. Okay, so specifically for the problems with the continuous state and continuous action spaces, DQN are showing promising results. So DQN performance depends on the articulation of the problems in terms of state, action, as well as the reward. We all know that. And the state represents the environment or the state of the environment. In this case, maybe building. So the cost of HVAC operation depends on the electricity pricing and the energy used for the HVAC operation. So this fact led us to hypothesize that the electricity pricing related features can improve RL's ability to observe the environment and to learn the optimal policy. One such feature can be next price change, time to the next price change. So in literature, electricity pricing have been used. Most of them used raw values and not specific, and not much attention has been provided to extract the specific features from the electricity price signals, which is the focus of our work. So now, since I laid the basic premise on the electricity pricing related features, in these slides, I will describe these features in detail. So this ST represents the state of the environment, where T represents the time of the day, T in T2 represents the indoor temperature, T out represents the outdoor temperature, and specifically PT and the PLAT represents the price related features. PT is the current price and PLA represent price look ahead features. So I will be explaining this price look ahead feature with the help of this diagram. So at any time TS, P1, which is the first feature, represents the price for the next time delta T1 until the next price change. And the T out average one represents the outdoor temperature during delta T1. Similarly, price P2 represents the next price. Delta T2 is the duration of that price. And we are also calculating the average outdoor temperature during delta T2. Now, along with these 6 features, we are also calculating an index called NDPI, Normalized Differential Price Index, just to capture how the price is changing, whether it is increasing or decreasing, and by how much magnitude. So this is the set of 7 features that we are using in this work. So using these state features, we trained RL model. So we use typical meteorological year data for Knoxville and use synthetic price signal. And then we perform training in the offline mode with the help of simulation environment. More details can be found in the paper. We used June data from TMY, and then we ran the training process for 50 episodes. At the beginning of each episode, we are generating random synthetic price signal by randomly selecting the peak start time, peak duration, and the price value. And then for validation, we selected 3 days from the month of August from the same TMY data. The sources for the data are also available in the paper. So this is the validation price signal that we use to validate the performance of the pre-trained model. So this slide shows the preliminary results of the validation experiment. So we ran validation for entire month of August and also evaluated performance for 3 days of the month of August, just to understand the day performance. So what we observed here is without RL model, without price look ahead, shows the 0 to 7% cost reduction over baseline, whereas with the RL model, which was trained using price look ahead, showed the cost reduction in the range of 12 to 15% over the baseline. So those results were promising. And also we observed that RL with the price look ahead tried to pre-cool the house just before the peak price. So that can be observed here in this in the bottom part of this figure. Okay. So those were our observation. Okay. So last slide. In this work, we tried to understand the significance of the price look ahead related features for RL training, and we observed the encouraging results, which shows the 12 to 15% of cost reduction over the fixed set point baseline. But there are still more need to do in terms of understanding the relevant features out of those 7 price look ahead features, and then more experiments need to be performed with the time of use price signals and the real-time price signals. Okay, so with that, I will conclude my presentation, and I would like to thank you for the opportunity, and I'm happy to take any questions.
Yeah, I'm so sorry. Like it's run a little bit over, and so I think we really only have 45 seconds or so for a question.
Oh, I'm sorry.
No.
Yeah, I'm happy to also chat over the Slack. Yeah.
I am curious why T, like your time, which I assume is just like an integer that integrates that just goes up, is explicitly part of your space base even though I assume the rest of your state space is also dependent on T, and the T just serves as like a linear incrementer.
So your question is the time of day that you're saying?
Yeah.
The state feature?
Yeah, you include a states feature T that I assume is correlated to the other state features and only serves to like fit a linear increasing
Yeah, I think that's a really great point. Yeah, you're very right in that comment. Definitely the outdoor temperature and sometimes if it is a constant price, if the time of use price, those two features then will be correlated with the time of the day. But if so again, I will go back to the concluding remarks to where we want to understand the importance of the feature. So out of this set of features, we can experiment with more data and try to understand which feature is putting significant impact on the operation of the RL training.
Okay, I'm so sorry, everyone. I think it maybe is time to start to move over to the other point, but there are actually a couple of really good questions in the chat. I apologize. There's like 3 different things that I'm looking at, and so I didn't realize that there's these questions in the chat. For the next 2, if people have questions, can you please unmute yourself and ask them during the question and answer time? Otherwise, they might be missed.
Thank you so much.
Yeah, but thank you so much. I really appreciate it.
Yeah.
Okay, so next up is Anjikin. And so Anjikin is a final PhD student at the Energy Institute at University College Dublin. They're passionate about using machine learning and data-driven techniques to make the world a more sustainable place. It's great, just like the rest of us. Fantastic. His research is looking at the use of data-driven predictive control in buildings, including both model-based and model-free techniques, thereby harnessing energy flexibility to allow for the increasing of renewable energy penetration in future smart grid, the future electricity smart grid. He's particularly interested in a comparison of model-free and model-based optimal control strategies and the robustness and scalability of the techniques over a heterogeneous building stock. Anjikin completed a BE at University of Auckland, New Zealand, and is specializing in mechanical engineering. They're a WEF Global Shaper, the president of the UCD ASHRAE student chapter, part of the UCD Sustainable Energy Community, a leadership network member of the Asia New Zealand Foundation, and a Rotary Young Leaders Reward recipient. And if you're ready, Anjikin, you are free to take it away.
Thank you, Lucas, for your introduction. Hopefully you can see my slides there.
We can see your slides, absolutely.
Perfect. Greetings to you all. My name is Anjikin Koganathan, and like Lucas introduced me, I'm a PhD student at University College Dublin, finishing off my PhD. I'd like to acknowledge my co-authors who were also part of this presentation and work. So today I will be talking about our submission to the City Learn Challenge that was held earlier this year. And the aim of this competition was really to develop, design, train and tune a reinforcement learning agent to flatten and smoothen the aggregated electricity demand profile for a district of buildings. And I guess I started off with model-based approaches in my PhD, but I've been tempted into the world of model-free reinforcement learning. And even after a year in, I have to say, sometimes I still feel a little bit overwhelmed by it all. So I just skipped a bit introducing this because we've had a bit of context already from the previous speakers. But I guess reinforcement learning in particular is very promising because it proves to be an automated control framework that can take feedback from occupants, which is especially important in terms of thermal comfort, and also its potential as a model-free and adaptive control of the buildings. And this is important because no one building is the same in the heterogeneous building stock. However, if we look at literature to date, most studies only focus on single buildings and especially demand-independent price signals. Finally, literature also shows that, especially in the building energy domain, that deep RL has often been limited to discrete and low-dimensional action spaces. So it's these which really motivate the City Learn Challenge hosted by University of Texas, Austin and BuildSys'20. And the aim of this competition, again, was for this district of 9 buildings to minimize these 5 different objectives for the microgrid, essentially, which included ramping, load factor, average daily peak demand, the electricity peak, and the total energy consumption by controlling domestic hot water and thermal storage cooling for these buildings. So just elaborating, it's an open source environment with the mix of commercial and residential buildings with pre-computed energy loads from Energy Plus. This just shows the particular archetypes of buildings used, but I will keep going. So in our research, we decided to focus on the soft actor critic algorithm. Now, we initially did experiment with other algorithms which are suitable for continuous action spaces, such as DDPG and DPG, but we noticed quite brittle performance, especially with regards to the hyperparameters. So we decided to settle on the soft actor critic algorithm for this challenge based on its relative robustness that we observed. The SAC algorithm we use is essentially an off-policy maximum entropy actor critic algorithm proposed by Han Oja in 2018. So it's a policy gradient method. Essentially, you have an actor which develops a policy, and then you have a critic estimating the value function. So we developed a PyTorch implementation based off previous work used in different domains. In terms of the reward function, we assumed a, I guess, virtual price based off the total electricity demand for the district multiplied by scaling factor. And then the reward function is a combination of this virtual price multiplied by the electricity consumption for each individual building and the summation of that. Now, we found that we had to apply some essentially manual reward shaping to help the agent essentially charge the thermal storages at night and discharge during the day. And this is something I'll talk about in a little bit later as well. We show the hyperparameters that we used after a bit of a sensitivity study, and we found that we had to essentially modify some of these hyperparameters on evaluating the agent compared to the training stage. We used a centralized agent with complete oversight of all 9 buildings, and the state space was composed of proxy variables such as month of day, day of week, hour of the day, as well as some ambient weather conditions such as solar radiation and ambient temperature, as well as states of the storage devices. In terms of results, we compare the agent with the manually tuned rule-based controller. So a score of less than 1 indicates better performance. And we were able to achieve this after about 10 episodes of training. In terms of performance objectives, this resulted in an improvement of about 10.57%, averaged over the 5 cost objectives I mentioned before, when applied on the same climate zone. So as this figure shows, the curve in red shows that we were able to flatten and smooth the aggregated demand to some extent. Now, one of the focuses of the City Learn Challenge was also on the adaptability of the reinforcement learning agent to deal with different buildings and different climates. So we were assessed essentially on the performance of the agent on a new design data set that we hadn't trained on. And in this case, it features different climates. So this shows the performance of the agent on these 4 different climates. And again, we were able to achieve improvements of less than 1, albeit moderate or mild improvements over the 4 different climates. So to conclude and to provide the contributions of this work, I guess, we developed a soft actor critic, and it was able to reduce the 5 cost objectives on the challenge data set. So highlighting the potential as a plug-and-play style controller for buildings for demand response. Now, the scalability is unknown, especially considering our centralized solution. And this is something that we will look into for future work. A major limitation of this work is, I guess, the manual reward shaping we had to apply to get the performance we did. And I'd just like to add that the code is available on GitHub as well. In terms of future work, together with the beta team at Politecnico di Torino, we're looking at a decentralized approach instead to this problem. And then also in terms of my other PhD research, I'm also comparing the reinforcement learning agent with a data-driven MPC solution for a US Department of Energy large office virtual building. And that's using co-simulation with Energy Plus. Thank you very much, and it's a pleasure to be here, and I'd be happy to take questions.
Yeah, thank you so much, Anjikin. That was fantastic. Does anyone have any questions? So
yeah, hi. Oh,
please, go ahead.
Yeah, so I had a question. Yeah, thanks for the very nice presentation. So yeah, I wanted to know your opinion on how in the future there will likely be more energy storage because of electric vehicles, and what impact that might have in the way we coordinate the energy storage of different buildings and settings.
Yeah, I guess good question. In our case, we did not really look at the capacity of the storage devices, but I think one of the brilliant aspects of the CityLearn environment is you can easily conduct sensitivity studies or different studies with different values of capacity and look at the, I guess, adaptability of the agents to deal with buildings with different capacity storages or increased storage capacity. So I think that's definitely future work, and it's certainly, I guess, something we just didn't have the time to look into. But I think, yeah, having the tools available to look into these research questions is very important, and I think we're getting there in terms of having the environments to do this research.
I'm very curious if I could ask, what was the most challenging part of this work for you?
I guess for myself, I'm a mechanical engineer. So in terms of the computer science and algorithmic elements of RL, I find them quite challenging. Certainly the training time was a bit of a challenge at the start, but we were able to get access to a cluster here at University College Dublin, and that definitely helped speed up training. But I guess this was also promising in that, you know, in this particular case, we found that 10 episodes was enough, which was quite a minimal, I guess, computational burden.
Cool. Thank you so much, Anjikin. Please, let's see a brief round of clapping reactions from everyone on Zoom. And I think we'll move to our final presenter of the day, which ironically, Anjikin's work is around the CityLearn environment. And now we're going to hear from the creator of the CityLearn environment, Jose. Jose is part of the group of Dr. Nagy. Jose is a postdoc researcher at UT Austin, working at the Intelligence Environments Laboratory. And he does research in the field of multi-agent reinforcement learning for demand response, which in some circles is a very controversial field. He received his PhD in civil engineering at the University of Texas at Austin, and he has a background in building energy management and power systems. He plays tennis and he hikes. And I have to say that in addition to technical skills, he has a very important scale, which is being a social researcher. He's very responsive and very, very helpful in interpersonal communication. And so I highly recommend reaching out to him if you want to chat about RL or his general work. And so with that, take it away.
Okay, let's see. Okay, can you see the screen properly now?
Yep.
Yeah, okay. Yeah, thanks a lot for the introduction. So yeah, my presentation will be on benchmarking different multi-agent reinforcement learning algorithms for building energy demand coordination task. So yeah, first a bit more about the big picture. So buildings account for 40% of the global energy use and 30% of greenhouse gas emissions. And in the US alone, they consume almost 70% of the electricity, which is a lot of energy. And even though we need to reduce it, it's not only important how much energy we consume, but when we consume it. And in this chart, we can observe a phenomenon that is known as the duck curve, which happens when there is a lot of solar energy generation. And even though solar energy generation helps reduce CO2 emissions, it also creates very sharp peaks and valleys, so in the daily load profile, which are difficult to satisfy with other sources of generation. So the objective of demand response is to modify the energy consumption of storage in order to better align the peaks of renewable energy generation with the peaks of energy demand and reduce the cost of electricity and improve the security of supply. However, one of the problems is that electricity is a commodity that has a very high value to price ratio, and for which consumers will be willing to pay between 10 to 20 times its actual price in order to use it. And this makes consumers in general unwilling to modify their energy consumption habits by much. And they also want to avoid, typically, having to constantly take decisions on when or when not to consume electricity. So these are some of the challenges for demand response, and therefore, demand response should provide its benefits in an autonomous way and trying to reduce any type of dissatisfaction by the consumers. So in our research, we implement reinforcement learning. So as well, it's been mentioned before, and it's a model-free controller that can learn from historical data and also through interaction with the environment, which makes it more cost-effective, since we don't need to develop models of the system that we are going to control. And that's why this is a type of controller that we are doing research in. And all the benchmark algorithms that are going to present here use the soft actor critic reinforcement learning controller that it was explained earlier in a previous presentation. So then, in order to prepare our benchmarking demand response scenario, we simulated a microgrid of 4 different buildings in CityLearn, which is the open AI gym environment that we developed for the implementation of reinforcement learning and for demand response and urban energy management. So the reinforcement learning controllers control the amount of heating and cooling energy that is stored in chill and domestic hot water tanks, which are provided energy by heat pumps and by electric heaters that consume this electricity from the same feeder in this microgrid. And the objective of the controller is to minimize the average of 5 evaluation metrics that we define here in order to measure how good or bad the demand response is. And then we also define a number of states that are based on weather conditions and the electricity consumption of the different buildings, and also the reward function. So we use a reward function that consists of the multiplication of 2 factors: an individual component that is based on the electricity consumption of each of the buildings, and also a collective component that is based on the net electricity consumed by the whole microgrid. or the net load of the whole network. And then in our paper, we analyzed 4 different types of multi-agent reinforcement learning controllers. So they all use the soft actor critic algorithm and the same reward function and the same states. But they are different in the ways they define and coordinate the different agents in this microgrid. So one of the agents that we tried was a central agent, in which a single soft actor critic agent controls the actions of all the buildings and knows the states of all the buildings. So a single agent knows everything and takes all the actions. Then we tested also the independent learner approach, in which we have a soft actor critic algorithm for every building. And they only know the states of that building, and they only take actions for that building. And these agents act independently of each other. Then we try a different approach, in which, well, as we know from the previous presentation, the soft actor critic algorithm has actor networks that take actions and critic networks that evaluate how good or bad these actions are. So in this approach, it's a mixture between a central agent and the independent learners. So we have decentralized actors that take the actions on different buildings, and we have a centralized critic that evaluates the actions of all the different agents. And then we also tried a value factorization approach with QMix, which is an algorithm for which I leave the reference here. But basically it's even more decentralized than the previous one. So it has many different agents that are decentralized, and the critic networks are also decentralized, but they are aggregated into a combined critic network to estimate a total Q value for the different actions. And then we tested all these algorithms, and we trained the controllers for 22 epochs and observed how the fully centralized agent performed the worst. And the independent learners performed surprisingly well to be acting independently without knowledge of each other. And then the value factorization approach with QMix algorithm, and the decentralized actors and the pseudo decentralized critics perform the best of all of these. So here we can see a trend towards decentralization. So decentralization helps improve the learning speed because we don't suffer from the curse of dimensionality. The agent doesn't have to learn from all the states of all the agents that we have. And therefore, by decentralizing the different agents, we can fight a problem that is known as the curse of dimensionality. So here we can see for a given I think it's 10 days or 2 weeks, we can see how they were able to flatten the curve of demand. So the main takeaways here are that decentralization improves scalability, improves performance by fighting the curse of dimensionality, and it's better overall when we have a large number of agents and we need to implement it in a real setting and not just a simulated setting in which we need to learn very fast and we cannot simulate the same thing again and again. So thank you very much. And now, yeah, leave it open for questions.
Could I ask a question? Is that already okay?
Sure.
Mm-hmm. Sure, okay. So thanks, Jose, for your talk. I was wondering, well, you were trying to tackle a big problem of demand response on a global, or at least on a larger scale. For example, you showed a plot of California, if I remember correctly, in one of your first slides. I was wondering, why is that CityLearn challenge relevant for representing this overall goal of solving demand response in that setting?
So the main idea is to, well, first we have a problem in reinforcement learning research for demand response or for other engineering problems, which is the lack of standardization. And if we have many researchers trying to tackle different problems with different types of algorithms. So the main idea of the CityLearn challenge was to have a same environment or a same problem, and that many different researchers can try to tackle. So it's not about making this environment as realistic as possible, because for that we would need to add, the power grid, the voltage regulation, and many other factors that are taken into account into real world demand response. Although over time we want to keep adding complexity to CityLearn and including electric vehicles or even some other aspects. But yeah, the main idea here is to see how reinforcement learning can start to tackle this problem, and how many different algorithms can be benchmarked and compared against each other in order to start taking steps towards demand response. And I don't know, does that answer your question? So,
kind of. I think I get the point of view. I guess you have to get started somewhere, though. I was wondering, like, I was checking your papers and your poster on BuildSys last year, so, but I didn't find no explanation why your selection of buildings or your building setup, like device configuration, is meaningful, or is it like something that is happening all the time, or that is the configuration that will solve that problem in a larger scale because it would be applicable to a large number of buildings, for example.
So again,
so if you haven't.
So we do this as a proof of concept to try to see whether reinforcement learning is able to start to manage the energy storage, whether it's thermal storage or whether it's batteries or electric vehicles, which we will start adding into CityLearn. And to be able to see if it's able to adapt to different types of storage devices or to energy consumption profiles. So it's not really, so our plan is not to simulate an actual city in California and to prove that, right now we are not there yet, like into trying to do it in a very real scenario. We are just trying to provide a setting in which that researchers can use to try different reinforcement learning algorithms and prove that they can work for this type of systems, if that makes sense.
Thank you.
Yeah, so something important is that right now many buildings don't have a high amount of storage. So sure, it's not maybe realistic to assume that every single building, residential building, is going to have this type of thermal storage for cooling and heating energy. But in the future, we will start seeing an increase in storage, either with batteries or electric vehicles, and every residential building will probably have one at some point. So we need an algorithm that is able to coordinate all this storage capacity. And I think reinforcement learning is a good option. So we are trying to have an environment that allows people to start doing research on this and comparing their algorithms with each other. And yeah, in order to prove that it can work in a reliable, somewhat reliable way.
Thank you.
I really want to thank Jose a lot. His work has provided the groundwork for a lot of work, including some of my own. And I want to thank everyone who's presented and everyone who's asked. Obviously, everyone in here knows that 7-minute presentations and 2 Q&As are really bad, just in terms of amount of time. But I think we're scheduled for a break right now. I'll defer to Dr. Nagy.
Yeah, thank you, Lucas. Thank you, everyone. We have made up all our time, so we will, which is great. So nobody was, listening to empty sounds. So I would suggest that we do take a break, just because it's scheduled and you may need one, to breathe a little bit, and then we'll reconvene 5 minutes past the hour, whatever hour that is for you in any of your time zones. So that should be 2:05 in Eastern, 1:05 Central, and then wherever you are in Europe or Asia. I'll see you then. And then if there is questions, please go ahead, use the chat. Go ahead, use the Slack channel and keep conversing. And then the official program starts at 1:05. 5 minutes past. Thank you.
lobby, one hall in a building, and we assume 15-minute control slots. Every 15 minutes, we send a control to the thermostat to change its set point. The state itself is the past zone air temperature, that is the indoor temperature in the zone observed over past several slots, and the outdoor air temperature also observed over several slots, cloudiness and cooling load in the building that was observed over several slots, and more high-level time of the day, day of the week information. And we also use forecasted information such as what is the outdoor air temperature going to be over the next several hours and what the cloudiness is going to be. With this state, the action itself is we discretize the set point axis within the comfort bounds. So every time slot, there's a comfort bound. During occupied period, comfort bounds are 22 to 24 degrees Celsius, whereas unoccupied is going to be 20 to 26. So we discretize those axes, and thermostat set points are based on that axis. And the dynamics itself is a zone simulator. We built our own thermal simulator, which we use as our dynamics model, underlying dynamic model, which we don't access. The agent doesn't have access to it, except that it engages with it as a real building. And the reward itself is made up of multiple components. One is the energy cost itself. We assume a time of use tariffs, and you can see I don't have to go into each of these notations, but at a high level, it's the cost per energy consumption times the energy consumption itself, and then there's a comfort cost, which is in dollar cost per degree hour comfort violation, and every time there's a violation above or below the maximum and minimum set point comfort bounds, we are going to have a cost incurred here, and the overall reward is just a negative of the combination of these costs. The total reward, this is again a sequential control problem, and we are representing it as a variant of Bellman equation. Essentially, we are saying the total reward is a combination of the immediate reward and the future reward defined by the current state and action. And the process itself is a partially observable Markov addition process based on this tuple state action, dynamic reward, and the discount factor gamma. This is a POM DP and not an MDP. If we had access to the internal thermal mass of the building, that is at any point of time, we know exactly the temperature of the air inside the building, all the objects inside the building, then that's all we need to define what the next state is going to be based on the thermostat set point action we take. But that's not something we are measuring. So we only have proxy measures like internal zone temperature and the various outdoor conditions over past several time slots. That makes it a partially observable Markov addition process. Yeah, so here's the agent that we are adopting. This is the double DQ1, pretty classic from 2015 paper. So we have this single zone simulator, and for any action, it gives a reward, and the action, the current state and the next state, all of them go into this experience replay buffer, and we have tuples, experience tuples, which are used to train the Q learning. We also maintain a target network, and then we have action processor to shape the actions based on our domain knowledge, and the cycle repeats. So our for the original POM DP, our DQ1 performance over a baseline policy, which is essentially pick the highest set point, came out to be something close to 2.32% over 5-year period, and there is definitely room for improvement. We believe that the complex state and action space that we chose could have led to learning issues, and that has to be significantly changed. And one thing that we know is that cost is driven mainly by the difference in electricity price for on-peak and off-peak. If the prices are the same, there is no optimization here. There is no need to shift the load. So shifting the load is going to be an important aspect of this optimization. And the important information that we need to do that is the time of the day. Knowing the time of the day and the corresponding tariff is going to be the most critical piece of information that we need to do this optimization. So we define this restricted POM DP, essentially a super trivialized state space, which is just focus on time of the day and day of the week. And the action itself is not multiples points in the bound space, but just the upper and lower comfort bounds, and retrain the DQ1. And we find that we get about 2 to 3 times increase in performance gains, which is what you're seeing here. And just to look at how this performs, it does do a pre-cooling around midnight. It goes to the lowest temperature, and then around 7 a.m. when occupants start coming in, it goes to the lowest temperature for that period, which is 22. And then when on-peak period tariff kicks in, we go to the highest temperature. So it does the pre-cooling pretty effectively just using the time of the day. So the high-level idea is that the lower bound, the gains that we have are actually lower bound optimal performance under the original Form DP. The one we show under restricted Form DP in itself is a viable policy because we don't, suppose we don't know what the exact time of pre-cooling.
Sorry to interrupt, but we're soon going to have to mute if we exceed the timing, just so you know.
Okay, so that's fine. That's pretty much it. So the idea is state and action space matters very much. Instead of just focusing on improving the agent learning, it's always a good idea to look into domain knowledge, domain heuristics, and define the state space and action spaces that are consistent with our knowledge. And we do need to have more study on what additional state and actions are can be added without challenging oral learning and how much the performance value is. That completes the presentation. Thank you.
Thank you so much.
Given we are overrun on this talk, we will save the Q&A later for the panel discussion and move on to the next talk. Thank you.
Thank you.
So the next speaker is Gautam Biswas. He is a professor in the Vanderbilt University at the EECS department. His research focuses on deep reinforcement learning, unsupervised and semi-supervised anomaly detection methods, and online risk and safety analysis applied to air and marine vehicle, as well as smart buildings. Professor Biswas, please start.
Thank you very much. I hope you can all hear me and see my slides. So what I'm going to talk about today is developing a deep reinforcement learning controller for non-stationary systems, assuming buildings are non-stationary systems, and I'll talk about that. And therefore, we might need relearning to keep the performance of the controller in sync. So my co-authors are Abhishek Nag, who's a graduate student working with us in computer science, and Marcos Quinones Guerrero, who is a visiting faculty at Vanderbilt University. I would also like to acknowledge our plant ops who are allowing us to use Vanderbilt buildings as living test beds. So all these controllers that we are developing, we are actually deploying in office buildings at Vanderbilt. So just to get started, buildings are important, and as has been mentioned in previous talks, they consume about 30 to 40% of the energy worldwide. So therefore, reducing energy consumption in buildings is important, but it's a complex problem because we are having to balance between energy reduction and comfort of occupants in the building. So therefore, it makes sense to try, to apply sophisticated reinforcement learning methods to try and build efficient controllers for buildings. So buildings operate in non-stationary environments for a variety of reasons. The internal operations of the buildings themselves are non-stationary, because conditions of the equipment in the building might change, faults might occur, occupancy levels might change unexpectedly, and environmental conditions change too, because there are weather patterns, but weather patterns are often violated. So I show on the right that, whereas you could have normal profiles of occupancy, certain events could cause those occupancy levels to change unexpectedly. Similarly, that could happen for the weather too. So given that we have to model building energy consumption as a non-stationary process, which means in our case, we are keeping the states and actions the same, but the transition probabilities could change, the reward functions could change. But again, in this case, in what I present today, we are not going to try to relearn reward functions. So to get to the details of our approach, so basically, this is a deep reinforcement learning. We have a lot of data of about the energy consumption of our buildings. The particular office building we are working on campus is called Alumni Hall. We used about 6 months to a year's worth of data to learn the initial controller of the building using a deep reinforcement learning method, deploy the controller, observe the performance of the controller over time. And when we find that the performance starts degrading, we use recent experiences to relearn or to modify the model of the controller of the system and then relearn the controller. So another point I should make is because buildings are considered to be safety critical, not in the sense of aircraft or automobiles, but the plant managers at Vanderbilt wouldn't let us deploy a controller to learn online because there are no guarantees that we would not violate, for example, comfort constraints. So therefore, we've had to take a more conservative approach of learning the model of the energy consumption online, learning the controller from that model, and then deploying the controller, collecting experiences. So a whole process involves this initial offline learning and then not periodic relearning, but relearning when we find that the performance assessment is going down. Our reward function involves multiple components. One is, of course, the energy component of the building. Another component is trying to, we are doing centralized supervisory control. So we are only controlling the discharge air temperature into the building, discharge air temperature and humidity into the building. But we are trying to minimize the workload of the controllers or of the HVAC units in the different zones by sort of trying to keep the set point of the discharge air as close to the set points of the different zones so that they have to operate minimally. And so that's a second component, and then there's a third component, which is trying to keep the set points in the individuals or trying to keep the temperatures in the individual zones as close to the set points as possible. And so we go through this cycle. We use a regression function to determine the trend in the reward. So when we find that the reward is decreasing significantly, then we reinitiate the relearning as I've described before. And the building we are working in, I said we are doing centralized supervisory control. So we are controlling the discharge temperature and humidity from the air handling units of the building. They operate in two modes. When it's cold, it just heats the air. But when it's warm and humid, then it cools down the air and then reheats it back to a comfortable temperature before discharging it. And we honor these two modes, and our controller operates very well in both of these modes. So very quickly then showing you an example. Here we've looked at when unusual changes in the environmental conditions occur. So here is a case where in summer, there is an unusual drop in temperature in the outside temperature of and that causes, for example, the reward function to decrease significantly, as you can see here. As a result of which, we then relearn the controller, and then the new controller then sets the discharge temperatures to slightly higher values to compensate for the cold conditions outside, and as a result of which we find that there are significant energy savings with the relearned controller than if we had stayed with the original controller. The interesting thing though also is that after a few days, then the environmental conditions return to their normal environmental conditions, and the controller again adjusts to these conditions. So one of the points I want to make about this is the way we are relearning only from recent experiences, and but also including past experiences. So there is the issue of catastrophic forgetting does not occur. So we've run it on a number of situations where the weather conditions changed in unusual ways. So this was during a warm period, it becoming cold. We've also run it in situations in winter where you had unusually warm days for a period of time. And we've seen that our controller adjusts and is able to save energy. So very quickly to sort of summarize what we've approached, our approach, we've used trend analysis, so to trigger relearning only when it is required. And then we have this offline relearning approach where we relearn the model from recent experiences plus past data, and then relearn the controller from that, deploy, again, continue to capture experiences as we go along. We've avoided catastrophic forgetting. By doing this offline, we are able to sort of ensure that we don't violate safety constraints, which are mainly comfort conditions inside the building. And we have been successful in saving energy. So one of the questions, especially given the invited talk we had today, is could we, instead of doing this offline or off policy, could we do it on policy? By putting in constraints into the learning process so that we don't violate, for example, safety constraints. So that's something we are going to work towards now. Our controller is currently deployed online in Alumni Hall. We are collecting data about performance. And one of the things we want to do is deploy this controller in multiple buildings. So one of the future problems we look at is transfer learning to do parameter tuning, because no two buildings are alike. So I'll stop here, and I would be glad to answer questions if there are any.
Hi, Professor Biswas. There is a question from the chat that brought two questions. So the first question is, for the offline learning phase, do you use historical data to establish a simulator first and learn it with it, or you directly use off-policy PPO to learn from the data?
No, we learn from the model. So we learn the model, the dynamic model, which is, I didn't talk about it, it's a LSTM. And then we learn the policy from the model. And the advantage of that is then, the model, sort, as I was saying, it does, we relearn or learn in a way such that there is no catastrophic forgetting. So therefore, the controller we design is likely to be more robust and able to handle different conditions.
I think since we're running late, we will save the second question for a week. You can address the question in the chat, and we'll save more questions for the panel discussion.
Okay, thank you very much.
Thank you. So for the third paper in the session, we welcome Dr. David Biagiano. He is a research scientist at the Computational Science Center at the National Renewable Energy Laboratory. His work combines optimization modeling, artificial intelligence, and advanced computing in applications to computational problems in clean energy.
Okay, thank you. Can you see my screen okay?
Yes.
Okay, thanks so much. Thanks for the introduction, and thanks for having us. Again, my name is Dave Biagioni. I'm an applied mathematician at the National Renewable Energy Lab in the Computational Science Center, as was just said. And we, about a year and a half ago, looked at comparing model-free and model-predictive control methods for price-responsive water heaters. I'm going to preface this by saying I'm not a energy management or building specialist, but we did work with some folks who are at NREL for this paper. So I'm going to kind of present this more from the, hey, I'm an applied math person with a big computer, and I want to know whether it makes sense in this context to use optimization modeling and MPC, or these model-based, kind of at the time were sort of emerging model-based, model-free methods that could leverage supercomputing. And so I'll sort of talk about that towards the end. The question of why water heaters, why do we care about water heaters for this study? Well, turns out water heaters are a relatively untapped source of flexibility. Typical US household uses about 5 megawatt hours annually. This is based on an online calculator that there's a link down in the slide there. You can see where that number comes from. But basically, these are devices that use a fair bit of electricity every year for a given household. And we can think of water heaters from a certain point of view as a one-way battery. That is, it's a device that can store power as heat, but can't return it as electricity. Stored energy is rather used to optimize end user utility. And we jokingly dub this the cold shower cost, which I'll talk about more in just a minute. So the question we wanted to answer with this study was, given a deterministic but dynamic time of use price, could we exploit the flexibility inherent in a water heater to support the grid while avoiding unhappy users? And honestly, the kind of more important meta questions I think we were really interested in, this is kind of in our naivete of about a year and a half ago, we were sort of new to thinking about some of these modeling and control mechanisms, was like, what do we get by using a model? Is there any reason to go model-free? What are the advantages to doing a model-free method when you have potentially a reasonable model of your system that you could use in MPC? We also wanted to know, could we leverage advanced computing to directly attack the sample complexity that comes with doing model-free stuff? So those were kind of, I would say, the more important meta questions we were hoping to answer with this, which I think we were able to do to some extent. And so as far as the modeling and the assumptions we made with this model, we basically took the approach of using an error-free model of the device itself. And so it turns out we basically identified a model that was linear in the physics, but has binary on-off control with the deadband being modeled. So the deadband is illustrated there on the right of the slide. Deadband is it's kind of meant to make sure your device, thermostatically controlled device, doesn't wear out by turning on and off too rapidly. And so this actually introduces some complexities in the dynamics that are not necessarily there in many other household devices. But so we use this error-free model for the device operation. We wanted to really include stochastic disturbance. In this case, the disturbance comes in the form of water demand. There are many ways you can introduce disturbances for a water heater's operation, but we kind of focused in on just this one particular one because it's clearly one of the most important ones for water heaters. When is hot water being used? We don't have necessarily a great predictive model for that for the purposes of MPC. And so our philosophy here was, don't let the physical model error confound the comparison that we're trying to make, but rather focus on the importance of exogenous uncertainty in the form of water demand, the MPC forecasting and the look-ahead horizon, how those things affect control performance compared with the model-free methods. And so in the spirit of the clash of algorithms, like kind of pitting these two approaches against each other here on this slide, the MPC approaches we considered, we looked at actually a number of different ways of doing MPC for this problem. We used Gurobi as the optimization software to do this, so it's a really good performant, commercial grade solver. And I'm not going to walk through the details of the math here. Basically, we're modeling, we're allowing ourselves to model everything from perfect forecasting, so MPC, which knows exactly the physics and exactly the exogenous demand, but over a limited look-ahead horizon, all the way up to a two-stage stochastic program, which is kind of reflected here in this P superscript n in the objective function, and indexes scenarios. And so we actually did everything from perfect forecasting with a single scenario all the way up to multi-scenario forecasting, two-stage stochastic programming. We also modeled these kind of more complex looking constraints down here at the bottom are there to model the deadband, which is an important part of the dynamics of how the water heater operates. And so we compared this with our model-free methods, and I know it's not totally fair just to drop these up in the notation up here in the upper right of the slide, but this is kind of the RL formulation that we used. And we used a library called RLEM20, which used TensorFlow under the hood to examine basically using PPO, which I think everyone on this call is probably, it's been mentioned many times already just in the workshop today, with another black box optimization algorithm called evolution strategies, which really does direct policy search over the parameter space of the neural network mapping between actions and the episode cost. And so this is not strictly two RL methods, although ES is often called RL. They're actually two model-free methods, one of which is reinforcement learning. The other one is really just black box optimization. And so I'm not going to go through the details of these plots other than to say that you can, if you stare at them long enough, you can convince yourself that even with perfect forecasting, you need quite a long look ahead horizon for MPC to converge on the quote unquote optimal solution. Optimal here being defined by an MPC model with unlimited look ahead and no error in prediction and no error in the model physics. And so even if you have a perfect forecast of the exogenous disturbance, you actually need quite a long look ahead to do the right thing. And this is attributed, as I'll talk about in a minute, to the fact that there is a time of use price spike or a peak in the late afternoon. And if you don't look far enough beyond that peak, you can't really plan around it correctly. It takes quite a bit of time to solve these optimization models in the sense that they are mixed integer linear programs. And as you add more time steps to your look ahead and you add more scenarios in the case of the stochastic programming formulation, you basically are getting exponential growth in the complexity of solving this mixed integer linear program. This is just part of solving such an optimization problem. Even with a good solver like Arobi, you're going to see this. You're going to see this happening. The takeaway from this, the overarching takeaway from this comparison was that model-free methods demonstrated on average better control performance over a held-out evaluation set of days and are much faster to use online, orders of magnitude faster. This is owing to the fact that evaluation of the policy for these model-free methods is effectively a forward pass of a neural network, which can be done very, very rapidly. And so I was personally interested. I know we got some feedback from reviewers. These pictures had way too much going on. I totally agree with that. But I really wanted to understand what it was that reinforcement learning and ES were doing that is so different from MPC. What are these things actually doing differently? What's the agent actually learning to do? And so we drilled down to two different scenarios. One was a high peak demand day, where you can kind of see in the lower right, the peak power price is indicated by this gray bar. And there's actually quite a bit of demand occurring, is indicated by these gray spikes during the peak price period. And so in this case, MPC actually does better than the model-free methods because it's predicting demand to occur and it's planning around it. It's willing to take a little bit of expensive power during this time to avoid accumulating cold shower costs, which you can see ES actually allows this to happen. You can see in the middle pane, this growing sort of blob of orange spikes indicates the cold shower costs are accumulating now because the ES agent is allowing the temperature to drop to be quite cold and users are getting cold showers.
I want you to know your overtime.
Okay, I will wrap up by saying what we learned is that evolution strategies, which by the way, we trained on about 1,100 CPU cores in about 90 seconds. So we really were able to train up a very fast policy. It basically learns to preheat before the peak price and then turn off during peak price. And so is that a useful strategy? I think it very much depends on the nature of the data and what you expect to really see happening in the system. But we were able to kind of hone in on the fact that's what the agent was doing, whereas MPC first had a more nuanced sort of scheme depending on how good the predictions were that it was making about the water demand. So with that, I will stop talking and say thank you very much for having me. We'll take questions in the chat or whatever is appropriate.
Thank you, Dave. I think we will move on to the next talk and leave the questions for the final panel discussion. And for the next talk, it's a paper from PNNL, and the presenter is Junyoung Lee. Junyoung Lee is a research scientist at the Bioinformatics and Data Science team at the Pacific Northwest National Laboratory. He currently works on deep reinforcement learning-based electrical load forecasting and reinforcement learning-based building control for the PNNL Transactive Control Project. Jun, you can take the floor.
Thank you. Can you hear me?
Yes, I can hear you.
Okay. Can you see my screen?
Yes, we can see your screen.
All right, so thank you for kind introduction about me. And today I want to share our like a preliminary work at PNNL. And we are working as a team. So we have a brilliant team member here. So they are experts on building simulation and building control and machine learning. I'm pretty much newbie in the building area. So I learned a lot of things from these guys. So as you already, many people already mentioned before, the Deep RL has achieved a great success in diverse fields. So as you know, such as the gaming AI, robot control, autonomous vehicle, and so on. So since RL has been highlighted as an emerging control technique, RL has been demonstrated its potential to improve building control performance. As already mentioned in other talks, the diagram shows the typical workflow of the RL-based building control. For the building control, RL controller has been applied to generate a series of optimal control actions by running an optimal control policy from interacting with environments with multiple trials and errors. Here, XT represents the measured state information at time t, indicating the building conditions such as the room temperature, airflow, and so on. RL agents model, usually the deep neural network model nowadays, represent the control policy modeled as a conditional probability of control actions by given states. Which is to generate the optimal control action U with the given state xt or a series of historical states. And then we should measure the reward from the environment and measure the state transit by the given action. So using the next state, we can select the action again, and iteratively we can update the parameter of RL models to maximize the long-term rewards. First here, we just try to implement the RL algorithms by ourselves to test the RL-based control for our system. And we realized that it takes so much time to implement everything from scratch, and it's not easy to find something, unfortunately, find something that we can immediately apply to our applications, since there is a tight coupling between the already implemented RL frameworks and building models. So here, we just want to implement the RL-based building control framework more flexible enough to quickly prototype and test the RL controllers for target buildings in various conditions by decoupling the RL systems from the building models. It's not fully decoupled yet, but we could decouple building systems in terms of these user parameters. Of course, users can customize the gym environments and building models. At the same time, gym environments are designed to allow users to customize the control variables and observations for the target building. Users also can select the target time frame, for example, like days of years for simulation. Moreover, user can customize the normalized function and reward function and RL optimization algorithm. So we are basically employed the open source Python packages like OpenAIG and OpenAI baseline without reinventing the wheels. And we also employed the high fidelity hybrid energy plus Modelica building energy model using the functional markup interface, which enables to exchange the information between dynamic building models. And everything is can be deployed with the Docker image. So to demonstrate the proposed the flexible framework, I was asked to test the reinforcement running based controller for the typical large office building at Chicago area. So it has the 12 identical floors with the 5 zones on each floor, and HVAC system has 1 chilled water system and 1 hot water system and 12 variable air volume system for each floor. We want to control the chilled water temperature set points and 3 discharge air temperature set points for the bottom floor and middle floor and the top floor. Observation parameters include in our case study, the observed parameters include outdoor temperature, supply air temperature, and so on, so far. And typically for the thermal comfort, we measure the predicted percentage of this satisfied, shortly like a PPD value. So we formulate the real function by incorporating the energy conservation and thermal comfort as shown in this equation. For calculating the whole building energy consumption, we consider the boiler gas consumption, hot water pump power, chilled water pump power, power consumption associated with 2 cooling towers and condensers, and so on. For the case study, we set up the weight values same as 1. And second term penalize the average occupants discomfort in all the zones like this. So these figures shows how to the RL algorithms, like a PP, we applied PPO and A to C performed for a 5-day period during 2 summer months, June and August, in Chicago area. And RL-based controller are trained using the RL framework we developed, and using the environment for the continuous action space. Baseline control here represent that we are using the manually tuned temperature set points without RL-based control. So PPO2 is a proximal policy optimization algorithm, shows a little bit better performance with the same RL agent neural network models. At the optimal episode, the episode with the maximum reward for the given RL model, A to C and PPO2 model improves on the baseline values of the total energy savings. We observed that at the optimal episode in June, especially the 4.4% of the total energy consumption reductions. For the August, the reduction in energy saving and marginal improvements in average PPD for PPO2 are 2.2% and 0.21%. And also we observed that the sum of the control actions converged to the baseline control parameter values actually. Here, this figure shows the average energy consumptions in various subcomponents between baseline control and RL-based control. In this figure, we can observe that the chiller power is significantly reduced in PPO2 case compared to the baseline case, which is partially the
out of time.
Okay.
Compensated by the increase. So yeah, so this here is my conclusion. So we implemented and demonstrated the flexible RL-based building control framework using the open source packages, and then we are still working on the incorporating the hyperparameter optimization and model inference modules. Thank you. Any questions?
Yeah. Thank you, June. There isn't a question from the chat, but I have a question. So I think the simulation environment you created is very interesting. And when I was reading the paper, I didn't see a GitHub link for like accessing your environment. Is it going to be made publicly available?
Yeah, we are planning to make it publication in public, and then, but still, as I said, we are still working on that. So it's not yet fully coupled, decoupled. So we are working on make it fully decoupled, hopefully.
So now we will open up the floor for a panel discussion. And for the audience, if there is like some research generic questions related to the session, you can put it in the chat and I will read it from the chat. So to kick off the discussion, the first question I would like to ask is that since this session is on the clash of algorithms, and in all of your work, you're exploring different algorithms. So what do you see as some of the gaps for applying reinforcement learning algorithm into building control application? Is there anything specific in this application that requires more research or that is not directly transferable?
And just to clarify, this is a question to all of the presenters.
Yeah.
Yeah, I can jump in. I really enjoyed the keynote presentation because I think it kind of helped frame some questions that I've had, and I propose actually ways to solve some of those questions, some of those problems. That is, it's really common, at least at NREL, it's very common to encounter research teams that have a simulator and also an MPC model or some other optimization-based control model to control that system. And how you can kind of take that, in a way, it's sort of like a prior, right? I mean, if you're thinking about model-free reinforcement learning, you have to learn everything by interacting with the system. MPC models can be thought of as kind of a prior. And the question is how you get that information out of that model to maybe warm start or in other ways inform a reinforcement learning-based method, and also ensuring safety, which I think was a really cool part of that opening talk. So I think for me, that was I'm actively really interested in that question right now, looking for opportunities to work on problems like that, because I think in real world systems, you're going to find you often don't have to start from scratch.
If I could add to that, I fully agree about the 2 points you made. Those are issues that we are facing in our own work too. But recently there's been some very nice work on physics-guided deep learning, where you can incorporate, say, physical constraints into an LSTM network. So that's something that we are thinking of investigating. For example, since we are modeling energy, we have to make sure that energy conservation is satisfied. And there's no guarantee when we learn a LSTM model that that is true. So we are looking into ways in which we could do that. But yeah, those are interesting challenges that we are facing with working in real world situations. In addition to the fact that, we are working with much in real high dimensional space too. So that's another issue. You're muted. Yeah.
Does the other two presenters have anything to add on in their experience working with like testing out and comparing different algorithms?
So can I say something? Let me jump in. So in my experiences, when I just try to apply like a multiple different RL-based algorithms, and then I realized that depending on the problem, actually, they shows a pretty much different behavior. Mm-hmm. So another question is how we can optimize the hyperparameters and like the RL model structures. So because when I just try to run our simulation, like 5-day simulation, it takes so long time. And then when we think about the real world problem, so when we try to use a real building system, and then how we can solve these issues, how we can how can I say, the speed up to select the hyperparameters in the model structure quickly, something like that. That's really challenging to me.
So just to add to this, I wasn't able to make my concluding remarks. So let me use this opportunity. I think I agree with many of the comments now, in particularly Professor Biss was right. The physics-based models. I mean, we don't have to even go into sophisticated ways of incorporating physical constraints into a deep neural network like LSTM. In fact, if we know that there exist some heuristics that the domain experts have always been using for several years in the company or in the community, and we know how those heuristics are performing and what kind of states they're using, that could actually be a good starting point. Just take it from them and define our hyperparameters based on that, and then we can use that as our baseline and build on top. We can add more advanced state definitions and see how the performance improves, or sometimes it can degrade because it gets more, the loss function becomes extremely complex for an RL agent to maneuver. We can take it one step at a time, but going back to the basics, talking to domain experts and taking their insights on defining some of these hyperparameters can be a pretty good low-hanging fruit, in my opinion.
Yeah, I think the consistent theme that all the presenters agree on is that adding from like model-free reinforcement learning algorithm, we should be incorporating domain knowledge from our building control community so that we can make these algorithms more simple, efficient, along with more robust and safer. The other question, there is one question I think is very good from the chat that I think it is related to when we're comparing algorithms, what do you think, how would you select the metric for comparison? The specific question in the chat is that in the session, there are 4 different papers and 4 different papers opt for 4 different comfort metrics. So I think the important question is that how do we have a consensus on evaluation in general for reinforcement learning algorithms and specifically in this context for comfort evaluation? So it's like 2 questions. One is on evaluation in general. What do you think are the correct evaluation metrics and procedure to use? The other is more specifically with respect to comfort and how we as a community reach a consensus so that we can benchmark our work effectively.
I don't know if we need to have a consensus. I know that for benchmarking it is good, but if coming from the industry, different customers have different requirements. Some customers, say it's a hospital, they're pretty particular about temperature comforts, but some customers may not be as particular. So the way you translate that into an optimization, it can be either a constraint optimization where you have hard constraint imposed, or it can be a weighted optimization where you just give some penalty for violation. So I don't think we can even come to a single magical metric for benchmarking purposes. I think the only thing we should strive to is the algorithms that we develop are directionally correct. No matter what specific formulation we use for these comfort bounds, we are directionally going in the right direction. That's pretty much how we should try to enforce it. And for that, we should try our agents to optimize multiple versions of the same comfort violations. Try to have evaluate them for various choice of comfort metrics, and hopefully in most of them or all of them, the agent that we're building can do a pretty good job.
Yeah, the challenge I think we face to some extent is, sure, right, everyone in a building, needs to maintain comfort parameters, but at what level of granularity do you do that? Do you go into every room and make sure that whatever a person desires is what you can meet, or do you do it by zone, or do you try and do it in some average way across the whole building? And that's something that we have been thinking of now. In some cases, we are lucky because, especially in Vanderbilt, these buildings are very well instrumented, so we have a lot of data. But in many cases, that may not be the case. So even though you may want to, manage things at a certain level of granularity, do you have the data, to be able to do that? So these are really interesting challenges. And in general, I think reward functions should be determined by the goals, and not all of us all the time are we working on problems that have exactly the same goals. So.
I'll just throw in from maybe more of an applied math perspective that if you have a hard constraint on your system, I've seen some interesting recent work on kind of using dualized methods where you kind of solve reinforcement learning and then do dual ascent type updates to price parameters or Lagrange multipliers in your objective function that enforce hard constraints on the system. In that case, you don't have to be ambiguous about what that weight should be. There's an optimal value of it. And there's some interesting theory behind that too, I think, recently developed. That's very different than trying to attribute what a person or a user actually values for whatever resource it is they're using. That to me is a much more difficult question that I think often just comes down to a modeling choice. I would love to know if there's a more systematic way, but that seems to be what I've always found myself facing when it comes down to choosing those numbers.
Yeah, I agree. I think it's not only important to know what metrics we use to define comfort or what we try to optimize, but also the relationship between them, like how much weight or importance we give to comfort with respect to the energy. Because sometimes we focus a lot on energy, but yeah, if you take a hospital that you were talking about before, then sure, the energy consumption is probably just a small percentage of the total cost of that hospital, while salaries or other costs are much greater. So you just want to prioritize a lot to make sure that people are comfortable. And maybe for the building owner, energy savings is not maybe the main question necessarily. So by properly taking this into account, maybe it's easier to convince people to implement energy savings controllers into buildings by making sure that that we can guarantee that the comfort is always satisfied.
I think the common theme here is that to summarize the common theme here, there is a very user-specific and customized definition for comfort that is usually like based on specific building stakeholders' requirements that resulting in a difficulty in basically defining a universal comfort metric. And also another consideration, as Dave chipped in, is basically how you define your comfort will modify the difficulty of how you solve the optimization problem. So these are the two considerations with respect to how to define and also to add on the third point Jose is saying is that how much we should incorporate, how much should we weigh comfort into the balance with energy. So I think this is, all these taken into consideration, this kind of explains why it is hard to define a universal comfort metric, despite the need that if we have a single metric, it is easier for us to compare work with each other. So I think we had a very good discussion that we have seen like common themes chipping in. And I am not going to overrun too much to take a Hevia session. So I'm going to wrap up the discussion over here now, but then we can still use the chat and also the happy hour to continue the discussion. Thank you all.
Thank you, everyone. Let's take a 5-6 minute break and reconvene at 10 past, and then we'll start with the last session. Thank you.
Thank you.
Okay, thank you. Okay, welcome back, everyone. Let's start the third session of the day, keeping it real. My name is Hilya Zandi, and I'm chairing this session along with June Park as a co-chair. So we're gonna have 4 presentations here, each of them 9 minutes long. About 3 through 6 minutes through the presentation, I'm gonna interrupt you to just let you know that you only have 1 minute. You don't need to do anything, just ignore me, but it's just to let you know that you have only 1 minute left, and just we can respect the time and have a good panel discussion. So I'm gonna start with the first presentation, which Lucas Spanger is the presenter. So he is a 4th-year PhD student at UC Berkeley under Costas Espanos, which means that he is about 1 year away from the question, when will you be graduate, to become existentially troubling. He tries to develop reinforcement learning for green energy controls broadly. In the past, he has performed large-scale modeling at the Department of Energy Advanced Research Project Agency, ARPAI, where he plans to return as the program director. Lucas' long-term research interests are enhancing financial investment into advanced green technologies. Green energy is more than just a job, but a passion. Lucas has a tattoo of a wind power on his back and a tattoo of concentrated solar panel on his arm. He's the president of his 50% grad student co-op and an active member of the Radical Furry community in San Francisco. Check out his column on green energy at the Huffington Post on medium.com. So Lucas, the floor is yours if you want to start your presentation.
Yeah, just really quickly, this is the concentrated solar on my arm. You can probably guess which tattoo cost more per kilowatt hour. I mean, per square inch of ink. Just kidding. Anyway, here is my presentation. My presentation is entitled. You can see my screen, right? Yeah, okay. Augmenting RL with planning for optimizing energy demand response in a perspective experiment. So the purposes of these talks are to introduce Office Learn as an environment for RL, to introduce an RL agent that does well, and to talk about my future direction so I can invite collaboration. And so this is a lot, and so I'll try to go very quickly. Part 1, framing. I think everyone here is aware that like sometimes renewable energies generate too much, and sometimes grids turn this off. And I bring this up because I'm not sure if you know that California last year shut off 3% of its renewable energy resources for this reason. Some days up to 30%. So this is bad. But demand response is a way to deal with this, in which we offer prices throughout the day to incentivize shift. These prices are calculated with market supply and demand. They are not behaviorally optimized. So our question is, can we do this? Can we make it an AI agent that actually learns how to make the prices better and make them behaviorally optimal? So there, part 1, Office Learn, an OpenAI gym environment. And shameless copying and plug goes to the Nagy group for their CityLearn name. This is the flow of information that our agent goes through, and I'll go through each of these boxes very quickly. The state space. So the controller takes in grid prices throughout the day. It can also take in like yesterday's energy and some other details according to what you want. Our environment currently supports time of use pricing and real-time pricing with a day of prices and a year of prices. It outputs a transformation of these same exact prices. So A1 through A10 are different values between 1 and 10, and these can be modified to represent more than just one 10-hour day. Currently, we have a person that just responds to this in simulation, a fairly complex curtail and shift person. In the future, and now this is important, we will run this in experiment, and so we'll get actual data, and we plan to train generative models so that this this agent is simulating something a bit more realistic. Finally, our reward basically optimizes on the total price throughout the day, but we include a regularizer so that the agent doesn't just reduce energy across the board, but specifically during certain hours. So this pipeline is focused in an office environment, but really you can think of it generally as a system where an agent is trained to incentivize individual energy use in any context. So please, if this interests you at all, think about using it for whatever thing you're thinking of doing. Try it here. It's at this GitHub, conveniently packaged within a Docker, so very easily to install. And again, shameless copy from the Nagy group. Please look for an Office Learn competition sometime in the pretty far future. Now, part 2, the agent itself. We have demonstrated that a vanilla soft acritic architecture can run pretty well on this. It trains well through repetition, and it converges to a value. However, it typically trains within 12,000 iterations, which is 30 years. And so we need to improve on that. So the main thing that we suggest to improve on is planning. So we have constructed a planning model that mimics the office. The controller, the planning model learns from data that's generated, becomes better, and then the controller trains on that overnight again and again as many times as it wants to do better. If anyone knows of Dyna, suggested by Sutton in the 90s, this is similar to that. And in general, this seems to perform pretty well. Across the price signal environments that I've mentioned earlier, we see that the planning model beats the vanilla model in all cases. It's probably the most pronounced in the simplest case. So in time of use, pricing over 1 day, the vanilla models are on the bottom in orange, and the other models are on top, and they converge a lot faster. So this is promising. They converge within 1,000 times, which is great. That's like 3 years. However, in the future, some things we're thinking of doing. Right now, we're thinking of reducing the action space. So instead of outputting a 10-dimensional vector of prices, we're going to output the weights to a cosine series that represent these prices. We're dealing with a time series, so why not exploit the structure of a time series to make things better? If anyone has thoughts on this or has tried this, I'd really love to hear about that. So please let me know. Second, like I mentioned, we're conducting this in an actual experiment. We have an office in Singapore that has around 50% office capacity due to COVID. We were supposed to do this in July, but COVID. We expect this experiment to take 3 to 4 months. And then we'll have a lot of data on how individuals in an office respond to demand response, which as far as we can tell, does not exist anywhere. And we really have tried to find it. Generative modeling of office workers. Using this data, we hope to train a series of generative flow models so that we have an agent that can generate their energy demand profile throughout the day in a realistic manner. And finally, we'd like to try several different forms of multi-agent reinforcement learning. This is notorious for being very data heavy, so we're not really sure if this is going to be a success. But so far, we want to try multi-agents with centralized communication and mean field RL, potentially with Bingqing. Any other agents you're interested in trying? Please email me at Lucas_Stanger. Wow, okay.
You have 1 minute.
Cool. Well, I just finished. So does anyone have any questions?
Let me check on the chat. Okay, I have a question about the figure that you showed to have a comparison between the vanilla ones and the ones with have planning. So we can see obviously that planning is helping the learning process. In terms of computation cost and how slow are they different? I mean, I know they have the same almost number of iteration, but you can see the convergence rates for the planning ones is improving, but how about the computational cost?
That's a really good question. Step for step, they're equivalent, especially because in our simulated office workers, you're basically querying a function, which is very similar to what you're doing in the planning model. You're just querying a different function. However, in practice, because you'd be running the planning times many times during a single day and running the vanilla one once during a single day, you'd incur some computational costs. However, I don't expect this to be limiting, just because our step size a day is so long that you could really do a lot.
Thank you. We have time for one more question if anyone has any question.
Yeah, so I wanted to ask, so would there be an energy bill for the whole office that they pay to the utility? And then each person will have an individualized energy bill that they will pay to the office? Is that correct?
Basically, yeah, and that's a really good point, because under our current intuition of things, one of the reasons why individual energy consumption in offices is a problem is that it's you're contributing towards a common cost that you don't bear directly. So right. So in our framework specifically, we run social games where people compete against each other for prizes, and so in that way we individualize the bills. So we individualize costs.
So can the office make a profit, like increase the prices that is charging the occupants and make a profit out of it?
Yeah, there's several ways for the office to benefit financially. It will save energy. We have demonstrated this in previous experiments. And so the office can save money directly there. It can pass some of that money and that savings onto the workers in terms of incentives for doing this. And I guess if we were implementing what you're suggesting, and the office doesn't have to worry about its energy costs collectively at all, then I guess it would save plenty of money there.
So what prevents the office of charging 5 times the price of electricity to the occupants, for example?
There are some issues there in how to manage the cost of common resources like common lights. But I suppose in theory, nothing prevents the office from jacking up its prices to the consumers.
Thanks.
No.
Thank you, Lucas. Great presentation. We're gonna move to the next presentation, and we're gonna clap for you. Okay, so the next presentation is by Dr. Shuangui Zhang. He is a postdoc researcher from the Computational Science Center at the National Renewable Energy Laboratory. He received his PhD degree in electrical engineering from Virginia Tech. Currently, he is interested in solving energy system related control problems with deep reinforcement learning and other stochastic optimal control technique on high performance computing. The floor is yours. You may be unmuted.
Thank you, Chair. Can you guys hear me now?
Yes.
Okay, so can you guys see my screen?
Not yet.
Oh, okay. Looks like it's a permission issue again. Wow. Sorry about that. Looks like it required me to quit the Zoom and join back later. So, Chair, would you mind can we switch to the next presenter?
Sure.
Okay, I'll come back next round. Thanks for this, and sorry about this.
No, that's fine. Okay. Number 3, true.
Oh, 1 second. So I think I can share it now. Can you
go ahead.
See it?
It's coming.
Like
yes.
Okay. Do you see my slides here?
Not a slide. I see your security and privacy things.
Okay.
You're on the right track then.
So let me see. I'll share the new screen. So I set this one and share. Yeah.
Okay. Yeah. We can see that.
Okay. Great. Sorry about this. So I'll be quick. Strictly 7 minutes. So Hi everyone. My name is Xiang Yu. I come from the Computational Science Center. And today I present a paper on behalf of our team here. And our title is Transferable RL for Smart Homes. So our motivation is that we would like to see in the real-time price DR market, what is the best way to implement a smart home optimal control in an affordable manner. So affordable means the answer to this question will be beneficial to both the grid and the homeowner. So the state-of-the-art technology nowadays are mostly based on the MPC, and which can successfully achieve the optimal control. However, the intrinsic feature for optimization-based method oftentimes prevent them from being cost-effective in the real-time implementation. So the task for this paper is we would like to investigate the feasibility of using RL to develop smart home controller and explore how to train them at scale using transfer learning. So we envision a edge and cloud integrated framework, just look like this. On the edge side, we have the home, and in the home, we have IoT devices collecting the building operating data, plus some occupants preference data. And when the data is prepared, they will be uploaded to the cloud where we will build a simulator. And using this simulator, an RL control policy will be trained, and it will be downloaded back to the edge side for control. So this is the loop for one building. What can we do if we have thousands of buildings, thousands of homes who want to have this service? The good news is that we can leverage the similarity among residential buildings because homes, they're similar from many different perspectives here. So our idea is that we can leverage the knowledge from an existing controller of a similar home to accelerate the training process for a new controller. Oops. So basically, we used a transfer learning. Our hypothesis is that for similar homes, their corresponding optimal controllers should also be similar, given that we already have a home H0 and we already have an existing RL controller parameterized by this. And given a new home, which are similar to H0, what we will do is we will warm start the parameter for HI using the H0 parameter. And then we will continue to use RL to learn this policy. For example, here we show the policy gradient method. And in contrast, if we use a pure RL without the knowledge transferring, we will randomize the parameter in this new controller. On the right-hand side is an illustration for the pure RL approach and the transfer learning approach. So if we use a pure RL approach, we will need to train a controller individually for each of the homes. And if we use transfer learning, we only need to learn the first one and then transfer the knowledge to all other similar homes. And by doing this, we hope we can save some computational resources. So to verify this idea, in the case study, we developed an optimal appliances scheduling problem, considering the uncertainty from the RTP. And the goal is to minimize the cost from occupants, discomfort, as well as the energy consumption. So we consider 4 typical home appliances, and each of them have a specific discomfort function and operating constraints. So we also use a real-world RTP data, and we formulate this optimal control problem into an MILP problem because all the appliances here, we assume they are on-off control. And the objective is to minimize this thing. And the first term is the discomfort, and second term is the energy consumption. So to train an RL controller to solve this problem, we first formulated into an MDP with a reward structure, which is equivalent to the objective function shown in the previous slides. And with the formulated MDP, we build an OpenAI environment and then use proximal policy optimization to train it on the NREL HPC system. So the RTP data that we use for training is from July, and we use first 10 days in August to test the performance. And here are the comparison between MPC and RL algorithms. And numerically, we can see that RL, it can achieve a pretty close average cost compared with the MPC controller. That means RL can have the potential to successfully handle this smart home control problem. So this is for one home. And so we have, what about multiple homes? So assuming that home is a home 0 and we already have a RL controller for it, So here we build some new homes, and which they are similar to home 0. Like home 1.1 and home 1.2, they're different from home 0 in the user preference, and home 2.1 and home 2.2, they're different from the appliances parameters, for example. And the home 3.1 and home 3.2, we basically add some or all the differences mentioned above here. And for all these 6 cases, we compiled the TL accelerated RL and the reinforcement pure RL in these 6 cases. And these are the learning curves showing up here. And we can see that by using TL accelerated RL, in many cases, we can save a lot of like computational resources, except these cases. So based on this, we have 2 notable observations. The first one will be TL plus RL is better than pure RL if we can give it a good starting point. And the second is that TL advantage does not change smoothly with the difference between the source and target buildings. And another way we can put it, like the home similarity indicating the TL acceleration is not proportional to the Euclidean distance in the home parameter space, which is a common idea of how we are going to measure the similarity of the home. And that just doesn't work out. So our next step will be like, what is the best way to cluster the home so that we can, based on their similarity, we can do the transfer learning. And lastly, I want to point out that we did use the transfer learning to transfer knowledge between RL controllers in this case study. And in another project, we did a similar idea, but we transferred knowledge between 2 different RL algorithms. We propose a global local policy search. Basically, in this case, we transfer the knowledge between an ESRL algorithm and a PPO algorithm to search a good control policy. So that concludes my presentation. Happy to take any questions. Thank you very much.
Thank you, Zhang. Great presentation. So you have a couple of questions on the chat. The first one is, how do you identify the similarity between the homes? Any physical metrics that you are using for this?
So in this preliminary study, we basically manually created all these homes which are similar to the home 0. So I say this is just a preliminary experiment so that we can see if 2 homes, they are similar, we can do this. However, in this paper, we didn't really come up with a good way to cluster homes to identify their similarity. But we do have a finding that, as I mentioned here, the Euclidean distance in home parameter space, that is just not good for such kind of similarity measuring.
Okay, you have one more question, but since we're running out of time, if you don't mind answer it on the chat box for Zoom, that would be great. Thank you.
Yeah, will do. Thank you very much.
Thank you. So the third presentation is, the presenter is Anand Krishnan, who is a scientific engineer at Berkeley National Laboratory and works in Building Technology Department. His research focuses on using network-connected devices in building for monitoring and advanced control to improve building operations. And he's also involved in several projects that study grid building interactions for demand response, resiliency, and load flexibility.
Hi, everyone. Let me share my screen. Cool. Can you see my screen?
Yes.
Okay, cool. Let me just start. Hello, everyone. As you saw throughout the workshop today, reinforcement learning has great potential to advance building operations and controls and help us transition towards a cleaner future. We've seen reinforcement learning controllers can be used to minimize costs, optimize comfort, and support the power utility. However, we do have to talk about the elephant in the room, the challenges researchers face when they attempt to deploy deep reinforcement learning-based controllers in actual buildings. Out of those significant challenges that have occurred during this process, such as integration with existing building automation system, dealing with faulty sensors, our paper focuses on the difficulties that arise due to the assumptions made during the training and development of a reinforcement learning controller, and we attempt to quantify the impact of these assumptions. My name is Anand Prakash, and I'm a scientific engineer. This work has been done by our team at Lawrence Berkeley National Laboratory. We developed and deployed our DRL controller at the FlexLab testbed at Berkeley Lab with the objective to minimize energy costs. FlexLab emulates a single zone commercial building with on-site solar generation and electrochemical storage. It also contains emulated humans, schedule-based lighting and plug loads, and the indoor environment is conditioned by an air handling unit. As training a DRL controller directly on a real building can cause damage to the equipment and discomfort to the occupants, we used off-policy learning to train our agent. We trained the agent on an OpenAI gym environment that used Energy Plus, Modelica, and functional mockup units to model the building envelope, the HVAC systems, and the distributed energy resources. Additionally, we also used 4 years of historical weather and electricity tariff data for training as well. We chose the deep deterministic policy gradient, or DDPG, as a DRL algorithm. As you can see, there are certain assumptions made in this phase that get embedded into a training agent. When this trained agent is deployed in the actual building, these assumptions can impact the control actions it generates, and the following slides, we look at them in more detail. Random seeds are used to initialize the agent during training, and 2 controllers using the same seeds would produce the same actions. Conversely, controllers using different seeds would produce different actions. The first assumption that we made was, with sufficient training, the variance in the actions generated by the controllers trained on different seeds would be negligible, and hence the process of choosing the seed would be hardly significant. However, this was immediately proved false. Out of 8 similarly configured controllers that were using the same hyperparameters but initialized with different seeds, only 4 of them converged. The distribution of the rewards of these 4 controllers are plotted on the left. Next, we choose 2 controllers with the most similar reward distributions, that is, controllers initialized with seed 1 and seed 2, and compare the actions they generated for our building. This can be seen on the figure on the right, where the significant difference in temperature set point generated for the supply air is quite evident. Moving on to a second assumption. We assumed that the building model that was calibrated using standard practices would suffice to train a deep reinforcement learning agent to produce optimal actions. Here, we have 2 controllers that were trained on 2 different building energy models, with the only difference between the models being the power consumed by the supply air fan. The figure on the left shows the fan power consumption from 2 energy models simulated with the same sequence of operations. The poorly calibrated model assumes that the supply fan consumes constant power irrespective of the command. It has to be noted that the supply air fan power is only 8.5% of the total building load. In spite of this small contribution, when the corresponding controllers were used to generate actions for the supply air flow rate in a building, as you can see on the figure on the right, the controller that was trained with the uncalibrated fan does not actuate the supply fan at all, irrespective of the state of the building. This is an illustration of how the inconsistencies between a simulated building and a real building can impact the performance of an algorithm. The final assumption that we studied also arises from the inconsistencies between the model of a building and the actual building. During training using the building energy model, it is assumed that the building equipment can condition the environment to meet the requested set point. However, in reality, this assumption hardly ever holds true. Due to the physical constraints or the lower level control sequence of the equipment, it may not even be able to reach the set point generated by the DRL controller. The figure on the left shows the supply temperature set point generated by DRL controller and compares with the actual temperature. Between 3 p.m. and 6 p.m., there's almost a difference of 5 degrees Celsius. We observed similar behavior in our battery as well. And to study how this lack of awareness of the physical constraints can impact a DRL controller, we compare the set points generated by the same controller in 2 different environments, one with the real battery and one using an emulated battery. The difference being that the emulated battery is able to reach the battery set point immediately. It can be seen that the emulated battery has almost a 10% higher state of charge during the periods of 3 p.m. to 9 p.m. And such incorrect state of the system can lead to suboptimal actions being generated. This table summarizes the differences in the actions generated for the AHU and the battery, and when the assumptions we made in training no longer hold true. The largest impact across all 3 set points arose from using a controller that was trained on an inaccurate building energy model. Preliminary evaluation also revealed that a controller that was deployed in a real building can incur more than twice the expected energy cost obtained from simulation. It is also important to point out that in our evaluations, we isolated these assumptions and studied them separately. This would not be a realistic scenario. To conclude, it is evident that the assumptions that were made during the development and training of a DRL controller can have significant impact on its performance in a real building. For next steps, we're looking at studying the impact of these assumptions when we use different DRL algorithms instead of DDPG. This might help alleviate some of the some of the issues we encounter when we use the random seeds. We're also trying to identify standard metrics to quantify the impact, quantify this impact irrespective of the problem objective and the algorithm used. And also we're trying to develop better training environments to incorporate the negative impact of these assumptions. I guess that's it, and thank you. I'll take any questions now.
Thank you for the great presentation. Let me look at the chat box. Okay, I still don't see anything. So I have a question for you. So basically this is very common whenever we want to deploy reinforcement learning, just to validate and pre-train the model in simulation environment and then deploy.
Yeah.
So based on your experience and the data and the information that you just provided to us, then how do you see us that what is the best simulation testbed that we can just pre-train our model before deploying it in the field?
I think any model that you train is going to be inconsistent with real world systems.
Okay.
So the some of the steps that we took was, after we had a model, we still did a lot more calibration when we identified we had issues. So the, when I said our model was calibrated using standard practices, we initially had a normalized mean bias error of less than 10% with the actual system. And in spite of this, we saw all these issues pop up. So the only way is like characterize the systems better, identify what control sequences are used in the system, and try to incorporate the control sequences into modeling also. So that might help, identifying that might help deep reinforcement learning understand the performance and the behavior of the equipment better. So better modeling basically and calibrating.
Thank you. Does anyone we have time for another question if someone has a question. Okay, I think we can go to the next presentation. Thank you. So Binking will be the next presenter. She is a PhD student from Carnegie Mellon University. Her research focuses on enabling real-world reinforcement learning for building control. And she won the Best Paper Award at BuildSys' 2019 for her prior work on this topic. So congratulations for the award. You can start your presentation.
Myself. Thank you, Helia, for the introduction. So the objective of this work is to introduce, wait a second. Let me make sure that I'm using the correct deck of slides. Oh, yes. Okay. Yeah, the objective of this work is to introduce off-policy evaluation as an essential prerequisite towards real-world reinforcement learning for building control. This work is motivated by a problem we encountered in our prior work. Previously, we proposed NeuraL, which incorporates domain knowledge on planning and system dynamics. Furthermore, we demonstrated that NeuraL agents pre-trained with imitation learning could match the performance of existing controllers, thus enabling real-world deployment of such agents using only historical data. However, it's less clear to us how imitation loss during pre-training translate to actual control performance during real-world deployment. To elaborate on this point, let me show you a specific example. Here, I'm showing the imitation loss during pre-training. While the imitation loss decreases over epoch, does that imply the energy and comfort cost decreases as well? Well, the answer, unfortunately, is not really. While the comfort cost decreases with the loss, the energy decreases first and then increases. This reaffirms our initial point that imitation loss does not directly translate to control performance. This motivates us to incorporate off-policy evaluation as an addition to our framework. Off-policy evaluation is the problem of estimating a policy's performance without running it on the actual system, using historical data from the existing controller. Off-policy evaluation is a classical method, and thus there is a lot of existing method. The question we are trying to answer in this work is that which of these methods are appropriate given the characteristic of building operational data? The challenge here is that most buildings today are still operated by rule-based control, which are deterministic policies. As a result, these policies only explore a very small portion of the state action space, as is exemplified here using historical data from a real-world system. After pre-training a policy, one would be interested in evaluating how well would the policy perform. Intuitively, this question is challenging because there is no observation for these state action pairs in our historical data set. In fact, this characteristic violates the minimal requirement of many OPE methods. For that, we refer you to our paper for more details. Given this observation, we need a method that can extrapolate to unseen state action space. Thus, we adopt the approximate model method, which use a data-driven model learned from historical data as a proxy for the actual environment. With the help of the model, one can extrapolate to unseen state action space. To validate our proposed approach, we use an energy plus model as a simulation testbed. This energy plus model is based on the actual environment on Carnegie Mellon campus. And in this system, we control the supply water temperature to a water-based radiant heating system to maintain the zone temperature. We use the simulation testbed to generate historical data and evaluate the ground truth performance of target policy. To demonstrate the generalizability of our proposed approach, we pre-trained 10 target policies with imitation learning. Firstly, we illustrate the use of our method on one particular target policy. Here, we are showing a comparison of the state and action trajectory of the same target policy in the energy plus model, as shown here in the blue line, and then in the approximate model, as shown in the green line. As you can see here, the blue line and the green line are qualitatively similar. This means that an approximate model may serve as a reasonable proxy of the actual environment for performance evaluation. At the same time, you can see that there is some discrepancy in the zone temperature between the actual energy plus model versus the approximate model, which will explain later why our evaluation of comfort performance is less accurate. Furthermore, we use bootstrapping to correct for bias and quantify uncertainty. The shaded green area shows the histogram of bootstrap estimates, and the blue line is the ground truth performance. As you can see, for the energy cost, the ground truth falls within the empirical confidence interval from the bootstrap samples, while the comfort cost does not. The reason is that bootstrapping accounted for parameter uncertainty in model estimation, but there are two additional sources of biases that it cannot account for. We also refer you to our paper for detailed discussion. Finally, we show a summary of the over the 10 target policies that we consider. On the x-axis, we have the ground truth performance, and on the y-axis, we have the estimate from the approximate model estimate. And the confidence here interval shown here is estimated using the bootstrap samples. On average, the approximate model method estimated the energy and comfort cost within a 1.84% and 14.1% error respectively. To summarize this work, The main objective here is to introduce off-policy evaluation to the building control community as an essential prerequisite for real-world reinforcement learning. An important intuition here is that the characteristic of building operational data present challenges for applying many existing methods to building control. The approximate model method shows promising results in this preliminary work and allows one to tap into existing knowledge on building models to make informed decisions on model forms and modeling methods. However, it by no means precludes the possibility of other more sophisticated methods being more suitable for building control. Finally, while the approximate model allows us to extrapolate to unseen state action space through its assumed model form, it also introduces a bias which is not corrected for using bootstrapping. Thus, further research is required to address this challenge. This is the end of my talk. Thank you.
Thank you. Great presentation. Let me see if the chat to see if we have any question.
I have a quick question.
Yes.
So your gray box kind of answered it for me, but I'm wondering in general, are the errors between your model and the plus model, right? Like is there like a predictable bias there, or is it random?
Is the question as to, if I interpret the question correctly, of course, that if you have a more accurate approximate model, the estimate is going to be more accurate. So the method is, the accuracy of the method depends on the quality of the model, if that answers your question.
Sorry, I'm so sorry. I wanted to leave time for someone else to answer a question, but my question was like, is there bias in this error? Like could you mention like a secondary model that that corrects for this bias, or like approximates between the output of your model and what you're trying to predict?
I see. So this is what I'm trying to kind of convey in my last bulletin point on the slide. That is that we basically, by assuming a certain model form, we enable extrapolation, but we are also introducing a bias through the functional approximation. And then like this bias is basically very difficult to correct using data alone, which is demonstrated by like the bootstrap estimate didn't manage to correct for that, because that's like a structural, we are making an assumption for the model form and we don't exactly know how that will impact our estimate using a data-driven approach.
Yeah, thank you for the good. Is it done with the question?
Okay.
Lucas,
does that answer?
Lucas?
I mean, I have, of course, I have follow-up questions, but no, please, like the floor is open for someone else for sure. I'll ask them privately.
Okay, yeah, thank you for your presentation. So yeah, I wanted to ask you if you think that the previous approach that you were using with imitation learning has any advantages with respect to this approach using off-policy and learning from historical data.
Yeah, so regardless, I saw that in your review. I think regardless of what method, whether we're using imitation learning or off-policy reinforcement learning, like they all face the same issue that you have a training loss. It's unclear how that training loss is related to control performance. So we basically, so off-policy evaluation is analogous to you having a validation data set during, say, supervised learning. The intention is to for validation. It is not for like training. And with regard to whether I think imitation learning is better or off-policy reinforcement learning is better, I think this is a very nuanced question, because then the question is, what am I comparing, like the state-of-art imitation learning method versus the state of...
Yeah, I was asking not if one is better than the other. That it seems that for what you are saying, the off-policy method is better. But if the imitation learning offers any advantage that the other method, learning from historical data, doesn't offer.
I'm not sure I got the question.
Yeah, I'm saying that if learning from some sort of model or other control using imitation learning has any advantage over just taking historical data from a controller and using an off-policy algorithm to learn from it.
Yeah. So the first point I'm trying to say is that this particular work is about off-policy evaluation. That is like a separate step from off-policy reinforcement learning. And the second question with respect to advantages versus disadvantages, what I was trying to convey is that I don't think there is a straightforward answer to which class of method is better. I think it needs to be answered on a algorithm by algorithm basis, because both are areas that are moving very, very fast. I can't compare behavior cloning to the state of art of policy reinforcement learning. That is not a fair comparison. Yeah, that's so. I guess the short answer is that I don't have a good answer to that question.
Okay, yeah, that's fine. Thanks.
Thank you, Binking, for the great presentation. We're gonna go back to the panel discussion. So if you have any other question, you can use through the either Slack or Zoom chat. So I have one quick question to just start the floor. So since the title of the session is Keeping It Real, so based on your experience and what you have seen, what is the main challenge you see to deploy reinforcement learning algorithm for optimizing at building specifically, because we are talking about building here at the scale. So what challenges you are seeing? And if you have any experience doing that, we will be happy to hear about it.
I could maybe take a stab at that.
Sure.
I think these are challenges. It's not just limited to deep reinforcement learning, but some of the main things are especially in our case where we use an off-policy learning and we had a model and we didn't use the data. Like, how do you know the model is good enough, first of all? And then how do you know it would still encapsulate all the different state action space that is necessary to train it? So I think an approach to solve this was using a lot of data, and hopefully it covers everything, but it still may not be. So I think there needs to be some sort of metric to determine, yeah, this is good enough, and this might help us at least set a starting point. I think Benching's previous paper, I remember Benching talked about training it on the real system to get some data and then start control. So that might be helpful too. I might have simplified it too much, but yeah.
Well, but yeah, I think Anand's point is very relevant. It's kind of what I'm trying to address, like trying to at least like trigger people to think about this problem. It's that regardless of what algorithm we are using, we can train way we're training at, we can have a policy. But then how do we know it's good enough? How do we know it's good enough? It's actually unclear, because we don't know if we are not sure if the simulation model is good enough, or if we're looking at some kind of training loss, we don't know if based on the training loss, we don't know how that translates to control performance. So whatever paradigm we are pre-training the agent in, there is a big question as in, how do you just at what point are you confident about a policy that you have trained? And then the next step is, how do you convey the expected performance to the building control, like the facility management, so that they don't just take your word on faith? You can actually give them something that is more tangible and like more, so you can make a statistical guarantee to them, so that like everyone has more to build confidence about these algorithms.
I have a quick general question for everyone, I guess. And I'm sure that you've heard of recent, like really exciting advances in the field of few-shot learning. And of course, like that domain is a little different. It's more like around more straightforward supervised examples. Do you think that techniques like that will eventually make their way over into like tools we use, like reinforcement learning nets that can actually minimize our data requirements?
Hi, Lucas. Could you repeat the new topics that is coming up? The name for that?
The name that I'm aware of is few-shot learning or one-shot learning. OpenAI, like OpenAI's GPT-3, I think made a lot of splash because as it increased the number of parameters in its net, it actually seemed to decrease the number of training examples needed, which is obviously like a constant critique of reinforcement learning.
Yeah, I think that corresponds to like the point that we discussed in like session 2, that by incorporating some kind of domain knowledge, whether it be like the incorporation of a model or prior experience of what hyperparameter works well, these are all things like we have like a large knowledge base of knowledge that can be incorporated to increase the sample efficiency. That's my take. And I think there are a lot of, basically there are many ways to approach the problem. Maybe like, as you said, field shot learning, meta learning, or transfer learning. These are all things that can be incorporated.
Okay, does anyone other of the panelists have any other ideas? Thank you everyone for your input, by the way.
I think Donghun has a question in the chat. Like, I'm happy to read it aloud if you'd like.
Oh, I can read it. Thank you. My question is that if reinforcement learning needs to build a simulation model for training, why don't we just build an MPC model?
So my answer is that reinforcement learning don't need to build a simulation model for training. That's kind of what I was trying to address in my prior work, that we can, by basically incorporating domain knowledge and by pre-training the agent with historical data, we don't need a high fidelity simulation to pre-train the agent. And of course, creating this simulation environment is extremely resource intensive. So I think it's an important problem to understand, how do we train reinforcement learning agents without the need for those models?
So I want to add on that. Another thing is that we can use some data-driven model, which can create, for example, if you have if you leverage, for example, the random forest, this kind of machine learning model, they can have very good forecasting property to learn the building thermal model. However, a lot of machine learning models like this, they're not differentiable. So in that case, you can leverage this kind of data-driven model in reinforcement learning, but not in the optimization-based approaches. So that is just one idea of why RL can be an advantage here.
Yeah, another advantage I think is that MPC methods are finite horizon models, right? Theoretically, reinforcement learning is learning over an infinite horizon, and it gets better and better if you have good reward functions. So that could be a difference too, right? So, like,
sorry, I'm not a panelist, but can I jump in? Yeah, so in terms of that question, right? I mean, weather data, anyway, in a mathematical framework for the reinforcement learning, we need to know all the state trajectory for an infinite horizon, but it doesn't really make sense, right? It's not just a matter of the prediction horizon because we don't know what's going to happen in the future, like 100 years later, in terms of weather and solar, right?
yeah, that's a good point, right? But that's why, for example, we do relearning, right? We know that we are not going to be able to predict all patterns in the future, but then if you can detect a change in pattern, you can then try to relearn. But then you have to be careful how you relearn. You don't want to do catastrophic forgetting because you don't want to forget what you learned before because those patterns will reoccur again.
Right, MPC does that because it's basically receiving horizon control. If something is not captured within the prediction horizon, and an MPC moves to the next step, and with the updated information, compensates the disturbances mismatch, and keep this those are kind of approach for the model predictive controls. So anyway, I just brought up those questions because I'm heavily involved in the MPC algorithm, and just my suggestion, maybe next time, I don't know, Jordan, maybe it's a good to involve MPC, the specialist or expertise, and have like a integrated MPC and reinforcement learning workshop, something like that, to identify which place we should go for the building operation.
Just a small comment to your work. I have seen MPC work where they actually relearn the model, data-driven model from at periodic intervals.
Right.
Then that addresses the problem we are discussing.
I also have like very limited knowledge comparing MPC and reinforcement, like not in the same building, but we've deployed MPC-based controls in a different environment, testbed as well. And we've seen that under like extraordinary or not seen before circumstances, for example, the fires that happened in California, like MPC is not able to find an optimal solution and just fails to converge. And this like produces really unoptimal set points for the building. And with my limited knowledge in reinforcement learning, what we've seen here is that it has the ability to better handle such unforeseen circumstances. So that could be an advantage. Like, for example, the MPC building that we had customers come call us and complain that people are melting and so are chocolates. So probably deep reinforcement learning might have a better, again, this is just speculation.
Yeah. So that's my question. Actually, at this moment, I don't think we solved every kind of a problem that works for every type of building. So I wanted to kind of identify what is the best solution for which type of building under what scenario. I don't believe like a reinforcement learning can cover every building and every problem. That's why I'd like to kind of include some of the folks from the model predictive control, because we have been studying like more than 2 decades in the MPC, and a lot of issue coming in this workshop has the same issue. I can hear like, what is the best model structure of hyperbolic space model, and like, what is the comfort index, how can we come up with the best like a baseline structure. Anyway, that's been discussed for decades in MPC the field. So I'd like to maybe involve some other expertise in the MPC and have a discussion together, not just
yeah,
right?
Dongwon, thank you very much, Lucas. For 1 second, Lucas, because I want to be mindful of your time, and we're 10 minutes past the scheduled time, and I know some of you guys are in Europe, and it gets later and later. But we're exactly where this conversation would be going in an awesome direction if we were to be able to continue it in a room. And before we do that, I do want to say, thank you, everyone. We had a great conversation. Thank you for the presenters. Thank you for the organizers. Thank you for the session chairs, those who put together the program. What I would like to do, there's two things. One is I would like to solicit some kind of feedback, whatever you want, put it in the chat, send me an email, put it in the Slack. Let us know, should we do this again? If we do this again next year, should we invite NPC people or not, as Dongwon suggested, just as a plug. I mean, of course we should be, and then make a bigger Clash of the Algorithm session, or what else you would like to see, and who would like to contribute, or who would like to be part of this bigger picture. And as we're closing out, the one thing that the BuildSys organizers have put together nicely is this interface called GatherTown. For those of you who checked it out, let me share quickly my screen and show you. So you will get the link in the chat box in 1 second. Right now, you can walk over there. You will need a Chrome browser. Put in your name, join the gathering, as it says. Oops, not this one. And then you will be in the conference room. How fitting. And you can navigate out of this in your 8-bit world. Go ahead. There, comment. Okay, so navigate out of this, because nobody wants to be in the stuffy conference room, of course, all day long. So we go to the outdoors. Let's move to the beach garden. You see there's people there, and you get the videos joining in. So move to the beach garden and enjoy the view and the breeze once it comes in. Here we are, Yokohama Beach. And hang out here at the beer garden. Put in your name, put something that identifies you as RLEM, so we can see you. Approach each other, and you'll see your videos showing up. Try to find the presenters. Presenters, maybe identify yourself if you're joining, so that people can find you. And then, I'll hang out there. I'll be back in a second, and then let's see where this conversation is going. And then everybody else, the papers are online. Get in touch if you have feedback. Use the Slack channel. It will be working until the end of the conference, at least. And then, get in touch, keep the community growing, and let's try to meet again next year at least, latest, and then, see where this is going. Thank you very much. This ends the session and the conference and the workshop. Not the conference, the workshop. Oh, one last thing, I'm sorry. Before I really let you go, since it has been mentioned in the Slack channel, there is one session in BuildSys that also deals with RL, and there are several posters at BuildSys that also deal with RL who were not presented here, and so there's more to see and more to talk to. And with that, thank you. Good night for those in Europe. Good morning in Asia, and it's happy hour in the US. So let's do that. Bye-bye. Thank you.
Thank you, everyone.
Thank you.